It is truly wonderful to have you spending your time here this evening. Before we dive into our discussion, I would be absolutely delighted to discover where in the world you happen to be tuning in from tonight. Are you nestled inside a perfectly quiet bedroom, perhaps riding along on a dark and sleepy train journey, or simply relaxing on a cozy couch while cradling a warm, comforting cup of tea? No matter where you find yourself right now, my sincere wish is that you feel completely comfortable, deeply safe, and entirely prepared to let your mind gently drift into a state of quiet contemplation. If you find yourself enjoying these tranquil, slow-paced explorations of the universe and wish to support the creation of more content like this, taking a brief moment to leave a like and hit the subscribe button truly helps this quiet little channel float along through the vast digital space. To those of you who have already joined our community and subscribed, please accept my heartfelt gratitude. Truly, your ongoing presence and support mean far more to me than words can ever properly convey. Now, as we turn our attention to tonight's topic, I will do my absolute best not to make the subject matter so gripping or intense that it winds up keeping you wide awake all night long. However, if it does happen to stir your curiosity and cause a bit of insomnia, you can at least rest easy, knowing you will come away with a far better grasp of why tiny particles occasionally behave exactly like rippling waves, and why the very fabric of reality seems to hesitate and remain undecided until an outside observer step in to watch it unfold. Honestly, gaining that kind of cosmic insight feels like a very small price to pay for a slightly restless night. So, let us settle in and begin our journey, shall we? What exactly is quantum physics? And why does learning about it so frequently make it sound as though the universe is simply inventing its own rules as it goes along? The everyday world that we are all familiar with, the tangible reality that we can physically see, touch, and navigate, feels incredibly solid, reliable, and entirely predictable. If you accidentally bump a ceramic teacup off the edge of a table, it falls straight to the ground. If you flick a silver coin into the air, it inevitably lands on one side. If you choose to close your eyes for a few moments, the moon up in the night sky does not suddenly vanish into nothingness just because you stop looking at it. Yet, as the early years of the 20th century began to unfold, a group of pioneering scientists resolved to look closer at the world than anyone ever had before. Much, much closer. And the deeper they managed to peer into the inner microscopic workings of matter, the stranger and more unrecognizable things began to appear. They made the startling discovery that light, which had long been categorized, could actually behave simultaneously, like a spread-out wave and a localized particle. Even more astonishingly, it turned out that subatomic particles could literally exist in multiple different locations at the exact same time, holding a myriad of possibilities until someone came along to measure them. Furthermore, the very act of observing a physical system did not simply uncover a reality that was already sitting there, waiting to be found. Instead, the introduction of a viewer actually seemed to alter the outcome itself. This was not some superficial error caused by flawed data collection, nor was it a technical glitch stemming from fuzzy, imprecise laboratory equipment. It was a real, deeply fundamental, and completely reproducible truth of nature. This realization utterly shattered the neat, orderly, and tidy laws of classical physics that had stood firmly as absolute truth for centuries. Quantum physics was far more than just a newly discovered branch of scientific study. It represented a completely radical way of perceiving reality itself, a strange, fluid, and shimmering version of existence, where absolute certainty is tossed aside in favor of statistical probability, and where cause does not always neatly precede effect in the linear fashion we naturally expect. Throughout the course of this video, we are going to drift gently and unhurriedly through that surreal world. There is absolutely no reason for you to strain your mind trying to grasp every complex mathematical equation, nor do you need to worry about memorizing every historical name we mention. We are intentionally going to move forward very slowly, softly, addressing just one cosmic mystery at a time. we will follow the timeline from the very earliest paradoxes that first nudged classical scientists off their comfortable, predictable perches, all the way to the modern, unresolved questions that continue to keep contemporary theoretical physicists awake at night. So, take a moment to tuck yourself in warmly under your blankets. Close your eyes if you feel comfortable doing so, and let us begin our quiet exploration of a reality where even total emptiness is not actually empty, and where every single thing you thought you knew about the universe is ultimately only probably true. As the 19th century drew to a close and the 20th century began, the field of physics felt almost entirely complete. The fundamental laws governing motion and mechanics were thoroughly understood. The study of thermodynamics was beautifully organized and tidy, and the behavior of light had been elegantly tucked into the grand framework of electromagnetic theory. It was a true golden age of intellectual certainty. A number of prominent scientists genuinely believed that every major question about the physical universe had already been answered definitively. From their perspective, only a handful of minor, eccentric anomalies remained to be cleaned up, like tiny specks of dust left behind in the far corners of an otherwise perfectly swept room. One of those remaining dusty corners involved an incredibly basic, everyday concept. What happens when you heat up a physical object? When you apply heat to a piece of metal or a lump of coal, it begins to glow. It shifts in colour as it gets hotter, turning first a dull red, then an intense orange, and eventually a brilliant white as the temperature climbs higher. This visible glow, which scientists formally termed black-body radiation, is the direct result of how material objects emit electromagnetic radiation when they are warmed up. It was something that anyone could easily observe in daily life, and it seemed like it should have been incredibly simple to explain using basic science. Yet, despite its apparent simplicity, the mathematics completely refused to cooperate. Classical physics, relying strictly on the highly trusted equations of that era, predicted a result that was completely bizarre and unphysical. According to those established formulas, as the temperature of an ideal blackbody increased, it was supposed to emit greater and greater amounts of energy at shorter and shorter wavelengths, causing the radiation to skyrocket, particularly within the ultraviolet spectrum. The immense problem with this math was that the prediction ultimately led to an output of infinite energy at high frequencies. This was a scenario so completely impossible, absurd, and disconnected from reality that scientists half-jokingly nicknamed it the ultraviolet catastrophe. No matter how much researchers attempted to tweak or adjust the classical equations, they could not prevent the mathematics from spiraling straight into absolute nonsense. The physical reality of the universe simply did not align with their theoretical predictions. It was clear that a vital piece of the puzzle was entirely missing. This was the moment Max Planck entered the story. In the year 1899, Planck was a highly respected German theoretical physicist who possessed a well-earned reputation for meticulous, cautious, and careful thinking. He was not by nature a radical thinker, nor was he looking to start a scientific rebellion. In fact, he was a firm believer in the classical worldview, but he was also deeply pragmatic. When confronted directly with the stubborn problem of black-body radiation, he decided to try something quietly revolutionary. In order to fix the broken math, Planck introduced a tiny, incredibly eccentric concept. What if energy could not actually be emitted or absorbed in just any continuous, arbitrary amount? What if, instead, it could only ever be transferred in tiny, indivisible, discrete packets? They would be like physical coins that you are completely unable to split in half. These individual packets would represent the absolute smallest possible building blocks of energy. He chose to call these individual packets quanta. This marked a monumental, dramatic departure from the smooth, continuous view of energy that had been held as absolute truth by classical physics for generations. Instead of a perfectly smooth, uninterrupted flow, energy would have to arrive in distinct steps, making tiny, sudden jumps that depended entirely on the specific frequency of the radiation in question. Planck even calculated and introduced a new constant of nature, now universally recognized as Planck's constant, to precisely define the mathematical size of these energy packets. It was an unimaginably small number, but it was mathematically elegant. The moment he plugged this brand new assumption into his radiation equations, something truly miraculous occurred. The problematic infinite energy calculation completely vanished into thin air. The equations suddenly worked flawlessly, and they matched the behavior of the real world with perfect precision. Planck had successfully resolved the ultraviolet catastrophe. Yet, despite his monumental success, he did not actually believe his own assumption represented physical reality. In fact, Planck himself openly described his historical solution as a mere mathematical trick, a clever, artificial way to force the stubborn numbers to behave, rather than a literal description of how the universe actually operated. He fully assumed that future generations of physicists would eventually discover a superior, more traditional explanation that would completely do away with such an odd assumption. To his mind, quantization was nothing more than a temporary patch, not a fundamental truth of existence. What he could not possibly have anticipated at that moment was that his desperate mathematical trick would soon become the definitive cornerstone of an entirely new era of human thought. His core idea that energy moves exclusively in discrete packets laid the indispensable groundwork for the birth of quantum theory, a theory that would very quickly unravel almost everything classical physics had taken for granted for centuries. It is quite easy for us to look back at history now and see this as the exact instant everything changed forever. But to the people living through it at the time, it felt much more like a strange, isolated side note than a grand scientific revolution. Planck had absolutely no intention of challenging the sacred foundations of his field. He simply wanted his math equations to make sense. And yet, by introducing the concept of quantization, he had quietly struck the very first match in what would slowly grow into a massive, slow-burning fire. One that would ultimately reshape our entire understanding of light, matter, and the fundamental nature of reality itself. This modest, unassuming beginning, tucked away inside a quiet academic paper published in the year 1900, did not loudly announce its own historical importance. There were no dramatic declarations made to the public, nor were there any sweeping, grand pronouncements. There was only a tiny new constant, a novel way of conceptualizing energy, and a highly curious little fix for a theoretical problem that had stubbornly refused to go away. From that pivotal moment forward, the field of physics would never quite feel complete or entirely finished ever again. By the early years of the 1900s, the behavior of light was thought to be exceptionally well understood by the scientific community. Thanks to the brilliant equations developed by James Clerk Maxwell, researchers had definitively demonstrated that light operated as a continuous wave, an elegant, smooth ripple moving through the electromagnetic field. It behaved exactly as any proper wave should, bending around obstacles, bouncing off surfaces, diffracting through narrow openings, and interfering with itself. Following Max Planck's quiet introduction of energy quanta, most mainstream physicists naturally assumed that things would eventually settle back down into a slightly adjusted, predictable version of normal. But then, the scientific community ran directly into a stubborn new riddle involving sheets of metal, beams of light, and an absolute refusal to cooperate with expectations. This phenomenon was known as the photoelectric effect, and it operated in a very specific way. When you shine a beam of light onto a clean metal surface, electrons can be physically knocked loose and ejected from the metal. On the surface, the basic concept made perfect sense. The incoming light delivers energy to the metal, and that energy kicks out the resident electrons. It seemed incredibly straightforward. According to classical wave theory, if you were to increase the overall brightness and intensity of the light source, you should naturally increase the amount of energy being transferred to those electrons. A more powerful, brighter wave ought to shake the electrons loose far more violently and effectively. That was the logical expectation. Yet, when scientists actually ran the experiments, that is not what happened at all. In laboratory settings, researchers discovered something deeply perplexing. Crank up the brightness of the light as much as they wanted, it did not increase the individual energy of the ejected electrons. What actually mattered, above all else, was the specific frequency, or color, of the light being used. If the light happened to fall below a certain threshold frequency, it could be incredibly bright, blindingly intense, and yet it would do absolutely nothing at all. Not a single electron would be released. Conversely, if the light was tuned above that critical frequency, even the dimmest, faintest whisper of a beam could knock electrons free with total ease. The boundaries of this threshold were incredibly sharp, and it made absolutely zero sense under the framework of classical wave theory. This minor experimental glitch rapidly ballooned into a full-scale scientific mystery. This was the environment Albert Einstein stepped into. In the year 1905, a period now widely referred to as his miracle year, Einstein published a groundbreaking paper that completely changed the trajectory of science by offering an explanation for the photoelectric effect. To solve the riddle, he proposed an incredibly bold hypothesis. What if light was not actually a continuous wave after all? What if, under certain specific conditions, it behaved precisely like a localized particle, a tiny, concentrated bundle of energy moving forward in a perfectly straight line? Einstein suggested that a beam of light was literally composed of independent packets of energy, which he termed light quanta, and which would later become universally known as photons. Each individual photon carried a very specific, set amount of energy that was determined exclusively by its frequency. If a single incoming photon possessed enough energy on its own, it could collide with an electron on the metal surface and instantly knock it free. If it lacked that necessary energy, it did not matter how many millions of photons you fired at the metal, nor how bright you made the beam. They could never get the job done. It was exactly like attempting to open a securely locked door with a massive handful of keys, not a single one of which actually fits the lock. It does not matter how many useless keys you hold in your hands, you are simply not getting inside that room. Einstein's concept built directly upon the foundation of Planck's previous work, but it pushed the idea much further into reality. He was not merely utilizing energy packets as a convenient mathematical trick to make equations work. He was explicitly suggesting that light itself was fundamentally made of these packets, not as a helpful fiction, but as a literal physical description of how light exists. It was a completely revolutionary claim, and a large number of prominent physicists deeply disliked it. Many scientists clung fiercely to the established wave model of light, and for good reason. After all, light undeniably demonstrated wave behavior in countless other scenarios. It clearly diffracted around sharp corners and created beautifully complex interference patterns when split. If light was truly composed of hard little particles, how could it possibly perform those wave-like actions? Einstein did not attempt to deny the well-proven wave nature of light. Instead, he proposed something far more radical and strange. Light, he explained, was simultaneously both a wave and a particle. It possessed the capacity to manifest as one or the other, depending entirely on the specific manner in which you chose to observe it. This mind-bending duality was not some superficial trick of human perception or a flaw in our senses. It was a fundamental, unyielding characteristic of light itself. Picture a golden beam of afternoon sunlight filtering gently through a bedroom window. To our eyes, it spreads out and ripples across the room like a continuous wave, bouncing off floating dust motes and reflecting off the glass panes. Yet, if you were able to zoom in incredibly close, past the limits of human sight, you would discover that the beam is comprised of tiny individual quanta of energy. Each one vibrates with its own distinct frequency, colliding directly into atoms and physically altering the world, one microscopic impact at a time. This profound concept of wave-particle duality stands as one of the absolute strangest ideas in the entire history of physics. This is not because the math behind it is overly complicated, but because it fundamentally challenges the basic mental categories we use to make sense of our everyday reality. In our classical world, things are strictly either solid particles or they are rippling waves. They cannot be both at once, they cannot be neither, and they certainly cannot choose to switch back and forth, depending on the situation they find themselves in. But the quantum realm does not require human permission to make sense to our intuition. Einstein's photon-based explanation of the photoelectric effect did not just match the physical laboratory data, It did so with breathtaking elegance. The precise energy of each individual photon corresponded exactly to its frequency, just as Planck had originally hinted, and it perfectly clarified why low-frequency light was entirely incapable of ejecting electrons, no matter how intense you made the beam. The individual photons hitting the surface simply did not pack enough punch to do the job. The cultural and scientific impact of this discovery was absolutely massive. In the year 1921, Albert Einstein was awarded the prestigious Nobel Prize in Physics. Interestingly, he did not receive it for his famous theory of relativity, as many people naturally assume today, but specifically for his brilliant explanation of the photoelectric effect. That fact alone demonstrates just how monumentally significant this discovery was to the scientific world. Even so, Einstein himself found the unpredictable, fuzzy nature of the emerging quantum world deeply uncomfortable. He famously spent much of his later life resisting the highly probabilistic interpretations of reality that other physicists began to develop. God does not play dice with the universe, he resolutely declared in a famous statement. Yet, whether he approved of the dice or not, the foundational rules of reality were rapidly shifting right before their eyes, and sitting directly at the center of those radical changes was an inescapable, beautiful truth. Light, the very phenomenon that illuminates our days and allows us to see our world, stubbornly refused to be locked inside any tidy conceptual box. It existed in discrete quanta. It danced through space as a spread-out wave. It collided with matter like a solid particle. It shimmered mysteriously between different states of being, revealing just enough of its nature to keep humanity wondering, and just enough to ensure we remain forever unsure. What began as a simple laboratory experiment involving light beams and sheets of metal ultimately shook the entire foundation of human physics. Because if light could behave this way, simultaneously continuous and discrete, spread out across space yet concentrated at a single point, what other profound secrets might be lurking silently in the quiet corners of the cosmos, just waiting to break all the rules? To understand this deeply, imagine the following scenario. You set up a simple table in a room, place a basic flashlight at one far end, and take a piece of ordinary cardboard with two tiny parallel slits cut into its center. You turn on the flashlight so that its light shines directly through those two narrow openings, and you look at the visual pattern that the light casts onto a viewing screen positioned behind the cardboard. On the surface, that does not sound particularly exciting or thrilling, does it? Yet, within this incredibly humble arrangement, consisting of nothing more than two small holes and a bit of light, we run face first into one of the most utterly mind-bending and profound experiments in the entire history of science. The double-slit experiment has achieved an almost legendary status within the physics community, and this is not because the setup is highly complex. In fact, it is almost embarrassingly simple to build. But what this simple test reveals about the nature of existence is anything but straightforward. Some physicists have jokingly remarked over the years that this stands as the most dramatic science experiment of all time, despite starring nothing more than a cheap flashlight and two tiny holes poked into a piece of paper. Let us first examine what our common sense tells us we should expect to see happen. In the traditional domain of classical physics, waves and particles operate in completely different ways. A wave, whether it is a ripple moving through water or a sound wave travelling through the air, naturally spreads out as it moves. When it encounters obstacles, it interferes with itself. Picture large ocean waves rolling toward a concrete barrier that has two small openings cut into it. The water waves will emerge on the opposite side of the barrier and begin to overlap with one another, creating a complex pattern of peaks and troughs where the ripples either reinforce one another or completely cancel each other out. That is the classic definition of interference. It is a thoroughly understood and highly predictable behavior. Now, let us contrast that with how solid particles behave. Imagine you are firing a stream of tiny rubber balls at a solid wall that features those same two openings. Naturally, some of the balls will pass cleanly through the left slit, while others will pass through the right slit. They do not overlap with one another, nor do they interfere with each other's paths. on the recording screen situated behind the openings. You would logically expect to see exactly two distinct clusters of impact points located directly in line with where the two slits are cut. That is classic particle behavior, completely straightforward and entirely free of surprises. So, what actually happens when you perform this exact same experiment using a beam of light? When scientists first directed light through the two narrow slits, they fully expected it to behave like a continuous wave, and that is precisely what it did. The light spread out after passing through the openings and cast a classic interference pattern onto the screen, a beautiful series of alternating bright and dark bands caused by the wave peaks overlapping and cancelling one another out in highly specific locations. So far, everything was perfectly fine. Light, exactly as Maxwell's equations had predicted, was behaving precisely like a wave. But then, the experimenters decided to make a change, and things got incredibly weird. Utilizing highly sensitive, state-of-the-art laboratory equipment, the researchers began to turn down the overall intensity of their light source. They dimmed it so much that the device was firing just one solitary photon at a time. Instead of a continuous flowing stream of light, there were now individual isolated particles of light making their lonely journey toward the two slits, one after the other. Now, according to all logic, you would fully expect these lone photons to act like independent particles. Each individual photon would surely have to choose to go through either the left slit or the right slit. If you were to wait long enough, allowing thousands of individual hits to gradually accumulate on the back screen, you ought to see two bright clusters form where the particles landed, looking exactly like the pattern left behind by those tiny rubber balls. But that is completely opposite to what actually occurred. Even when the photons were sent through the apparatus one by one, with long pauses in between them, they gradually built up the exact same alternating interference pattern on the screen as before. It was a pattern that absolutely required overlapping waves to interfere with one another. But how could a single, solitary photon possibly interfere with itself? Did it somehow split apart and travel through both slits simultaneously? Was it somehow existing as a wave and a particle at the exact same time? This was no optical illusion or mathematical fluke. The interference pattern stubbornly persisted, strongly implying that each individual photon had travelled through both slits at once, acting like a ghost of itself, exploring every single available physical path across space until the moment it finally landed on the screen. If that revelation was not already enough to raise some serious eyebrows, the situation managed to get even stranger. Intrigued and confused, physicists decided to peek behind the cosmic curtain. They decided to place highly sensitive particle detectors directly next to the two slits so they could observe exactly which path each photon was taking. Surely, they believed, we can just watch the openings and settle this mystery once and for all. Does the photon actually go through the left opening, the right opening, or does it somehow find a way to pass through both simultaneously? But the moment they introduced those detectors, the interference pattern completely vanished from the screen. As soon as the recording equipment was switched on and the paths of the photons were actively observed, the light completely stopped behaving like a wave. They instantly began acting like ordinary classical particles again, landing directly behind just one slit or the other. There were no more alternating bright and dark bands. There was no more ghostly floating wave behavior. It was as if the very act of looking at the photon forced it to make a definitive decision. It had to go left or it had to go right. It could no longer exist in a superposition of paths, with no more fuzzy in-betweens allowed. Reality had been caught in the act of being undecided, and it immediately straightened up its behavior and began acting perfectly normal. Turn off the path detectors, and the mysterious wave interference instantly returned. Turn the detectors back on, and the wave pattern vanished once more. The philosophical and scientific implications of this were absolutely staggering. The core issue was not that our mechanical measuring devices were physically bumping into or disturbing the delicate photons. These were completely passive, non-intrusive laboratory setups. The problem was not how we were choosing to observe the system, but simply that we were observing it at all. It appeared that the mere availability of knowledge regarding the photon's path, the sheer potential to know which way it went, was completely sufficient to collapse its spread-out wave behavior into a sharp, localized particle state. Reality, in a very literal sense, seemed to care deeply whether it was actively being watched by an observer. This was not a temporary fluke or an experimental error. The double-slit experiment has been meticulously repeated countless times around the world using photons, electrons, and even massive molecules composed of hundreds of individual atoms. The result is always completely identical. Left entirely unobserved, these physical particles behave like waves and interfere with their own paths. The moment they are observed, they behave like classical objects and fall neatly into line. And if learning about this sounds deeply unsettling to you, well, you are certainly not alone in that feeling. This single experiment sits directly at the absolute heart of quantum physics, and it stubbornly resists every human effort to explain it using familiar, common-sense terms. It demonstrates that at the smallest scales of existence, particles do not follow clean, definite trajectories. Instead, they exist as a spread-out cloud of possibilities, a shimmering tapestry of potential outcomes. Only when a formal measurement is made does that cloud of potential instantly collapse into something definite and real. Over the years, different thinkers have tried to picture the photon as a physical wave that splits apart and reunites. Others prefer to use the strict language of statistics, describing the quantum wave function purely as a mathematical tool used for predicting final outcomes. And still others, belonging to the radical many worlds camp, imagine that each separate physical possibility actually branches off into its own independent parallel universe. But no matter which interpretation you personally prefer, the experimental facts remain exactly the same. Until the moment we step in to observe it, the particle simply refuses to commit itself to any single state of being. What started out as a simple, straightforward test of light has blossomed into a profound, unresolved mystery regarding the very nature of reality itself. Is the act of observation an active, necessary component in shaping the physical universe? Does information itself hold a fundamental power over material existence? Is reality at its core completely uncertain until we explicitly ask it to reveal itself to us? These are no longer just abstract philosophical questions discussed in coffee shops. They are concrete scientific dilemmas rooted in physical experimentation, measured precisely, and confirmed time and again. The double-slit experiment does not provide us with neat, comfortable answers, but it does grant us one powerful, undeniable insight. The universe, at its deepest core, is not a rigid clockwork machine. It is a strange, shimmering world woven entirely from possibilities, and it responds in highly curious ways to the gaze of an observer. Armed with nothing more than two tiny slits, a basic light source, and a viewing screen, we have discovered that the universe playfully winks at us when we are not paying attention, and stands perfectly still the moment we turn to look. In the extraordinary world of quantum physics, if there is one single piece of mathematics that has whispered its way through the entire theory like a secret, magical spell, it is undoubtedly Schrödinger's equation. Now, please do not worry or feel anxious. This is absolutely not going to turn into a dry, boring university mathematics lecture. No one is going to force you to get out of bed tonight to solve complex partial differential equations in your dreams. But this particular equation is fundamentally different from all the others you might have seen. It is not just a cold, rigid string of abstract symbols scribbled across a university chalkboard. It represents the quiet, steady heartbeat of the entire quantum realm. Back during the 1920s, the world's top physicists were wrestling desperately with how to accurately describe subatomic particles that did not seem to behave like solid particles at all. Electrons were showing clear, wave-like interference patterns in labs, while photons were acting like elusive, probabilistic ghosts. The old established laws of motion, the classic formulas that Sir Isaac Newton had gifted to humanity centuries prior, simply were not capable of cutting it anymore. The physical universe required a completely new kind of mathematical language. This was the moment Erwin Schrödinger entered the scene. In the year 1926, he proposed a brilliant equation that described not just how quantum particles moved through space, but precisely how their underlying wave functions evolved over time. It was wonderfully elegant, remarkably compact, and shockingly effective in its real-world applications. And even though it might look to a layman like a confusing tangle of Greek letters, mathematical operators, and variables, at its absolute core, it tells a very simple story. It describes exactly how a quantum system changes. But let us step entirely away from the abstract symbols and focus on what truly matters to our understanding. The central concept we need to explore here is the wave function, which physicists almost always denote using the trident-shaped Greek letter psi. If that sounds a bit too abstract for your comfort, try thinking about it in this visual way. The wave function operates as a sort of mathematical whisperer that holds and conveys every single piece of information we can possibly know about a given quantum system. It tells us where a particle might be located, how statistically likely it is to be found in that specific spot, and exactly how it is moving or might be moving through space. The crucial thing to remember is that the wave function does not provide us with hard, definitive answers. It deals exclusively in probabilities. If you were to picture a subatomic particle as a tiny, solid dot traveling through empty space, classical physics would draw a neat, sharp arrow indicating its exact position and its precise velocity vector. Schrödinger's world completely refuses to do that. Instead, it replaces that sharp dot with a hazy, rippling fluid cloud. A wave that essentially states, the particle is highly likely to be located right over here in this central area, but it also has a smaller chance of being over there, and perhaps there is even a tiny shred of possibility that it is located just a little bit up there too. This is precisely where the magic of the physics happens. Schrödinger's equation allows scientists to track and evolve this cloud of possibilities smoothly over time. It demonstrates exactly how the wave function transforms as the particle moves through its environment, though, to be more accurate, it is tracking how the shifting possibilities of its position flow and change. And the moment we choose to measure the particle, the exact instant we step in and ask, "Where are you right now?" that spread out wave function instantly collapses. Suddenly, the hazy cloud completely disappears from existence, and we are left with a single, sharp, definite answer. Here it is, located right at this exact spot. But that definitive location only exists after we have taken the time to look. This wave-based perspective of reality is profoundly and radically different from the rigid, mechanical, clockwork picture of the universe that dominated human thought for centuries prior. Instead of solid particles tracing perfectly predictable, deterministic paths like tiny planets orbiting around a central sun, we are forced to view reality as a swirling field of probability, full of fundamental uncertainty and ambiguity, until the sharp act of observation pins them down into a single outcome. But let us bring this abstract concept down to earth with a much more visual, everyday analogy. Imagine you are completely blindfolded and standing quietly in the middle of a room. Somewhere inside that room with you, there is a very quiet cat. Because of your blindfold, you cannot hear it moving, and you obviously cannot see where it is sitting, but you happen to have a pocket full of little rubber balls that you can gently toss around the room, listening carefully for the specific sound they make when they land. Over time, as you throw more and more balls, you will naturally begin to build a mental picture of where the cat is most likely to be located. You will map out areas with a very high probability of housing the cat, and other areas with far less chance. That detailed mental map you are gradually constructing in your mind operates exactly like the quantum wave function, is not a direct physical picture of reality exactly as it is, but rather a map of reality as it might potentially be. Now imagine that you are smart enough to write down a single, elegant equation that could perfectly predict how your mental map would change as time passed. Perhaps you know the cat naturally prefers to wander toward dark corners, or likes to sit quietly near warm objects like a radiator. That equation would serve as your definitive guide to predicting exactly where the cat is most likely to wander next. That is precisely what Erwin Schrödinger accomplished, except instead of tracking household cats, He was thinking deeply about the behavior of electrons. The actual mathematical equation he built is continuous, fluid, and remarkably smooth. It allows these complex waves of probability to ripple, shift, and flow, just like ripples of water moving across the surface of a still pond. It perfectly respects and upholds the deepest underlying symmetries of nature, such as the conservation of energy and the continuous evolution of time, but it does not care in the slightest for absolute classical certainty. It tells us exclusively what could potentially happen, never what will definitively happen. And what is truly fascinating to behold is just how beautifully and flawlessly it works in practice. Physicists have successfully utilized Schrödinger's equation to accurately describe almost everything in our modern technological world, ranging from the intricate internal structure of individual atoms to the precise way different molecules bond with one another, and from the behavior of semiconductors inside computer chips to the mechanics of superconductors. It even successfully predicts highly exotic, surreal phenomena like quantum tunneling, a bizarre process where subatomic particles are able to seamlessly slip right through solid physical barriers that they should lack the energy to cross under classical laws. The equation itself stands as something timeless, gently and reliably ticking forward with each passing moment, offering humanity a precise mathematical map of the otherwise unknowable quantum world. One of its absolute greatest historical successes was in perfectly explaining the exact mechanics of the hydrogen atom, which is the simplest and most basic atom in the entire universe. Before the advent of quantum mechanics, no scientist on Earth could fully explain why electrons orbiting around a central, positively charged nucleus seem to permanently settle into very specific, discrete energy orbits, rather than spiraling violently inward and crashing into the nucleus, or simply wandering off into space. Schrödinger's equation pulled back the curtain and revealed that electrons are not actually whizzing around the center of an atom like miniature, solid planets orbiting a sun. Instead, they form stable, stationary standing waves, beautiful, balanced patterns of probability that wrap completely around the nucleus. These are the famous atomic orbitals that you have likely seen drawn out as soft, fuzzy clouds or complex three-dimensional shapes in chemistry textbooks. And it is vital to understand that these drawn clouds are not just helpful visual metaphors or artistic choices. They represent the literal, physically measurable likelihood of exactly where an electron might be detected if you ever decided to step in and look for it. These are not planetary orbits. They are active zones of presence, and they exist in that fluid state exclusively because the electron is not a simple, solid particle. It is a rippling wave moving through a vast sea of probabilities. It is undoubtedly strange to think about, but it is also beautifully, flawlessly consistent. Unlike many other scientific theories that require awkward patches, arbitrary corrections, or special caveats to make them work in different situations, Schrödinger's equation has aged like a fine wine. It simply works. It has successfully predicted, time and time again, the precise behavior of the ultra-small world with an almost astonishing degree of accuracy. And yet, despite its immense practical success, it remains hauntingly abstract to our human minds. You cannot physically hold a wave function in your hands, nor can you ever see one with your eyes, but it is undeniably out there, quietly describing the ghostly potential of everything around us, from a single atom vibrating inside your warm cup of evening tea, to the complex electronic processes occurring inside the smartphone or computer you are using right now. And then, of course, there is the deep philosophical side of the matter. What actually is a wave function in reality? Is it merely an abstract description of our own limited human knowledge, or does it represent an actual physical part of objective reality, something that truly, physically exists in the universe, until the sudden moment it collapses into a single, concrete outcome? Different schools of thought and interpretations of quantum mechanics continue to argue fiercely with one another about this exact point to this day. But the mathematical equation itself refuses to take sides in our human debates. It simply continues to do exactly what it does, quietly, reliably, and beautifully strangely. Even Erwin Schrödinger himself famously harbored deeply mixed feelings about the implications of his own creation. While he was immensely proud of the mathematical framework he had constructed, he thoroughly disliked the philosophical notion that subatomic particles did not possess definite real properties until the moment they were actively observed by an outsider. His legendary, world-famous thought experiment involving a cat trapped inside a box, existing simultaneously as both completely alive and completely dead at the exact same time, was originally intended as a sharp, critical satire of the very absurdity and radical uncertainty that his own scientific work had unleashed upon the world. He successfully gifted humanity the definitive mathematics of quantum waves, and then spent much of his remaining time questioning what those waves could possibly mean in reality. Still, despite his personal reservations, it is incredibly difficult not to look at what he built with a profound sense of awe and admiration. In a human world that so frequently and harshly demands a simple yes or no, demanding that things be strictly here or strictly there, Schrödinger offered the universe something far gentler, a beautiful shimmer of maybe, a softly pulsing mathematical guide to what could potentially be. His equation does not loudly shout at us, nor does it issue rigid commands. It suggests, it blends, and it flows. And in doing so, it reveals a version of our universe that is infinitely quieter, subtler, and far more deeply mysterious than anyone before him had ever dared to imagine. At the ultra-microscopic scales of existence, motion is not always simple motion, physical position is not always position, and certainty operates more as an unobtainable luxury than an absolute rule. But thanks entirely to one remarkably elegant equation, we can still find our way gently, safely, and mathematically through the cosmic haze. In the familiar classical world that we navigate every day, the macroscopic domain of crunchy apples, moving bicycles, and heavy bowling balls, you can easily know exactly where an object is located, while simultaneously knowing precisely how fast it is travelling. It is not even a question that crosses your mind. A police officer's radar gun can instantly clock the exact speed of a passing car, while a basic GPS unit tells you its precise coordinates on a map. There is no mystery involved, no conflict, and absolutely no contradiction between the two pieces of data, but the quantum world completely refuses to play by those comfortable rules. During the mid-1920s, a brilliant young physicist named Werner Heisenberg introduced a core principle so deeply strange and so absolutely central to the framework of quantum mechanics that it still causes physics students and veteran scientists alike to pause and marvel. It is known globally as the uncertainty principle, and what it explicitly tells us is that at the most fundamental, deepest level of physical reality, there exist absolute, unyielding limits to what can ever be known by anyone. Specifically, the principle states this: the more precisely and accurately we attempt to measure a particle's exact position in space, the less precisely we can possibly know its momentum, and vice versa. Now, to keep things simple, momentum is just an object's physical mass multiplied by its velocity. It is essentially a measure of how much motion something possesses. And if you choose to think about this principle in terms of our everyday experiences, it sounds almost completely silly and counterintuitive. How could the mere act of knowing exactly where a physical object is located cause you to become entirely unsure of how fast it is travelling? If you are standing on a platform and watch a passenger train slowly pulling into a station, you obviously know both its exact location next to the platform and its precise slowing speed. It is easy, but at the ultra-microscopic quantum scale, the fabric of reality simply will not allow that kind of total clarity. It is absolutely vital to emphasize that this is not a limitation caused by our mechanical measuring tools being clumsy, crude, or imperfect. It is not a matter of humanity simply needing to wait for better, more advanced technology to be invented. The fuzziness and uncertainty are not located inside our laboratory instruments. They are actively woven directly into the very structural fabric of the universe itself. To visualize this, let us say you are a scientist attempting to observe a single electron. You want to pinpoint its exact location in space and discover precisely how fast it is traveling. In order to see it, you would naturally need to shine some light on it. But as we discovered from Einstein, Light is composed of individual photons, and those photons carry a set amount of physical energy and momentum. The exact instant one of those incoming photons collides with the electron so it can bounce back into your detector, it will inevitably transfer some of its energy, violently altering the electron's original motion. It is very much like trying to find the exact location of a delicate floating soap bubble inside a pitch-black room by forcefully throwing heavy tennis balls at it. You will undoubtedly find the bubble the moment a tennis ball strikes it, but you will also completely alter and destroy its original state in the exact same process. Still, Heisenberg's profound point went far deeper than just the physical act of disturbing a particle during a measurement. His uncertainty principle is mathematically built directly into the core equations of quantum mechanics. Even if you were somehow able to observe a subatomic particle without interfering with it at all, watching it through some hypothetical, ghostly, non-intrusive spiritual means, the fundamental uncertainty would still remain completely unchanged. It is not a bug in the machinery of nature, it is a permanent feature. At the deepest root of the uncertainty principle lies the fundamental wave nature of all quantum particles. Imagine trying to pinpoint the exact single location of a large wave rolling through the open ocean. You can point to where a specific crest is at a single moment, but the wave itself naturally stretches out across a wide area of space. In the exact same way, a subatomic particle, like an electron, is described by a spread-out wave function, a wide cloud of shifting possibilities. If that probability wave is exceptionally wide, smooth, and regular, you will be completely unable to say exactly where the particle is located, but you can estimate its wavelength and momentum fairly well. Conversely, if you force the wave to narrow down into a sharp, tight spike to pinpoint the particle's exact location, the wave becomes incredibly choppy and erratic, and its momentum becomes completely uncertain. It is an absolute cosmic trade-off, and there is no way around it. Mathematically, the product of the uncertainty in position and the uncertainty in momentum must always be greater than or equal to a tiny constant value, Planck's constant divided by 4 pi. Because that specific number is so unimaginably small, its effect in our macroscopic everyday world is entirely negligible. You can measure the physical position and the speed of a flying baseball to an incredible degree of precision without ever bumping into these quantum limits. But at the scale of electrons, individual atoms, and subatomic particles, the uncertainty becomes absolutely impossible to ignore. It completely shapes the behavior of the entire world existing beneath our physical senses. If you attempt to trap a quantum particle inside an exceptionally small space in a desperate bid to nail down its exact position, it will react by beginning to behave wildly. Its momentum instantly becomes highly uncertain, causing it to begin zipping around unpredictably at immense speeds. Try to pin it down even further, squeezing the boundaries tighter, and it will resist your efforts even more violently. It is as though nature itself deeply dislikes being told exactly where things are located. This is not an error in the cosmic machinery. It is a fundamental blurriness that can never be wiped away. To fully appreciate just how deeply bizarre this fundamental blurriness truly is, it helps to understand that this is the absolute reason why microscopic atoms can even exist in the first place without instantly collapsing in on themselves. Under the old traditional laws of classical electricity and magnetism, a negatively charged electron orbiting around a positively charged atomic nucleus ought to constantly radiate its energy away into the surrounding space. As it rapidly sheds that energy, it should logically spiral inward faster and faster, eventually smashing straight into the nucleus in a tiny fraction of a single second. If classical physics had the final say in how the universe was run, every single piece of matter in existence would instantly fold in on itself, and the entire physical universe would vanish into nothingness before it ever had a chance to begin. But the uncertainty principle steps in like a cosmic guardian to prevent that catastrophe from happening. Because if an electron were to get squeezed too close to the nucleus, its precise physical position would become exceptionally well defined. And as we have just established, the tighter you define its position, the more wildly its underlying momentum must fluctuate. The electron instantly gains an immense chaotic burst of kinetic energy, forcing it to violently kick outward and break free from the tight grip of the nucleus. This fundamental quantum trade-off creates a perfect, stable floor below which the electron can never fall. It establishes an absolute minimum size for the atom, ensuring that matter remains solid, stable, and completely safe from self-destruction. This strange, built-in fuzziness also gives rise to one of the most astonishing and surreal phenomena in the entire subatomic world, a process that scientists call quantum tunneling. Imagine you are holding a solid rubber ball and you gently toss it against a thick, solid, concrete wall. Every single time you throw it, the ball will inevitably bounce straight back into your hand. It simply does not possess anywhere near enough energy to physically penetrate or smash through that solid barrier. In our everyday, macroscopic world, that barrier is absolute and common sense reigns supreme. But now, let us shrink that entire scenario down to the quantum scale. Imagine that our ball is a tiny electron, and the concrete wall is a solid electrical force barrier. As the electron glides toward that barrier, it is not traveling as a sharp, localized dot. Instead, it moves through space as a spread-out wave of probability, smoothly governed by Schrödinger's equation. When this probability wave encounters the electrical barrier, the wave does not instantly drop to zero. Instead, it begins to decay exponentially inside the barrier, losing strength very quickly, but not entirely disappearing. If the physical barrier happens to be exceptionally thin, a tiny residual whisper of that probability wave can actually manage to bleed all the way through to the other side. This means there is a real, mathematically precise, non-zero chance that the electron will suddenly manifest on the opposite side of the wall. It does not punch a hole through the barrier, nor does it leap over the top. It simply disappears from one side and instantaneously materializes on the other, seamlessly slipping through a region of space that it should be completely forbidden from entering based on its total energy. It sounds like pure science fiction, like a magical teleportation trick out of a fantasy novel, but it is a thoroughly documented reality that happens countless billions of times every single second inside our modern world. In fact, without the reality of quantum tunneling, the sun up in our sky would completely cease to shine. The nuclear fusion reactions occurring deep within the sun's scorching core require two positively charged protons to come close enough together to fuse. However, because they both carry positive electrical charges, they repel one another with immense, staggering force. Under normal conditions, the immense heat and pressure inside the sun are actually not quite high enough to force those protons to overcome that mutual repulsion. The electrical barrier between them is simply too high and too thick, but because protons are quantum particles, they are capable of tunneling right through that forbidden zone, defying the classical energy barriers and allowing nuclear fusion to ignite the stars. Every single ray of sunlight that warms our planet and sustains all biological life on Earth is a direct, beautiful consequence of subatomic particles pulling off this impossible cosmic magic trick. Furthermore, this exact same surreal process is actively happening right now inside the palm of your hand or on your desk. The modern solid-state flash memory chips tucked inside your smartphone, your computer, and your USB drives rely entirely on quantum tunneling to store your digital data. When you save a photo, a document, or a video file, the device uses a small electrical voltage to force electrons to tunnel right through a solid, insulating layer of silicon, trapping them inside a tiny structure called a floating gate. Once those electrons are safely tunneled through, they remain locked in place, holding your digital information safe and secure until you choose to delete it. It is a deeply humbling realization to ponder as you lie comfortably in bed tonight. The very same bizarre quantum fuzziness that allows the sun to burn bright across the vast emptiness of space is also being quietly harnessed by human engineering to store the digital files on your phone. The cosmic and the mundane are completely bound together by the exact same set of strange rules. As the late 1920s and early 1930s began to unfold, these radical discoveries started to coalesce into a formal, unified framework of thought. Physicists could no longer view these strange anomalies as isolated, quirky exceptions to the rules of nature. They had to face the reality that a completely new worldview was being born, The epicenter of this intellectual earthquake was located in the quiet Danish city of Copenhagen, where the legendary physicist Niels Bohr operated a highly influential institute that attracted the most brilliant minds from every corner of the earth. Together with Werner Heisenberg and several other prominent colleagues, Bohr formulated what would eventually become known as the Copenhagen interpretation of quantum mechanics. For nearly a century, this specific viewpoint would stand firmly as the dominant mainstream way that scientists taught and conceptualized the quantum world. At the absolute heart of the Copenhagen interpretation lies a deeply profound and challenging assertion. It states that a physical particle does not possess objective, well-defined properties, such as a specific position or a definitive velocity, during the periods when it is not being actively observed. Before a formal measurement is made, the particle exists exclusively in a fluid state of pure potentiality, represented mathematically by its spread-out wave function. This state of existing in multiple potential realities at the exact same time is formally known as quantum superposition. The Copenhagen view boldly claims that it is completely meaningless to ask where a particle is located before you choose to look at it. It is not simply that we do not know its position, it is that its position does not exist in any concrete form at all. The particle is literally everywhere and nowhere all at once, rippling through a sea of possibilities. Then, the moment an external observer steps into the system and conducts a formal measurement, a sudden and dramatic event takes place. In an instant, the smooth, continuous wave function completely collapses down to a single point. All the other myriad possibilities that were shimmering in the air just a moment prior vanish into absolute nothingness, leaving behind a solitary concrete reality. This sudden transition from a spread-out wave of possibilities to a single localized particle is what physicists refer to as the wave function collapse, and according to Niels Bohr, the defining line that separates the fuzzy quantum world from our sharp classical world is the precise act of measurement itself. This interpretation immediately triggered an intense, decades-long philosophical battle that would permanently split the scientific community. The idea that objective reality depends so fundamentally on the act of observation felt deeply wrong to many traditional scientists, most notably Albert Einstein. Einstein was a passionate, unyielding realist. He firmly believed that the universe existed completely independent of human awareness or mechanical intervention. He found the notion that a particle remains undecided until a scientist looks at it to be utterly preposterous and deeply offensive to the core spirit of science. This intellectual clash led to a series of legendary debates between Albert Einstein and Niels Bohr, which took place during a succession of prestigious academic gatherings known as the Solvay Conferences. Einstein would arrive at these meetings with brilliantly constructed, highly elaborate thought experiments designed to expose internal contradictions or absurdities within the emerging quantum theory. He would present these challenges to Bohr over breakfast, trying to prove that a particle must possess definite properties all along, regardless of whether anyone was watching. Bohr would then spend the entire day in deep, agonizing thought, pacing through the corridors and conferring with his colleagues, only to return by dinner time with a brilliant counter-argument that successfully dismantled Einstein's challenge, using Einstein's own logic and physics against him. No matter how hard Einstein pushed, the quantum mathematics held perfectly strong. Yet, despite his inability to find a fatal flaw in the theory, Einstein completely refused to surrender his deeply held convictions. It was during these intense discussions that he uttered his famous immortal phrase, declaring that he simply could not believe that God would choose to play dice with the universe. To Einstein's mind, a theory that relied so heavily on pure statistical probability and lacked absolute determinism had to be fundamentally incomplete. He was convinced that there must be some deeper, hidden layers of reality, frequently referred to as hidden variables, that physicists had simply not discovered yet. He believed these hidden rules would eventually restore perfect order, predictability, and classical certainty to the universe, proving that the dice rolling was just an illusion born of our own ignorance. Bohr, however, remained completely unmoved by these complaints. In an equally famous and witty retort, he told Einstein to stop telling God what to do with his dice. Bohr argued that it was not the task of scientists to dictate how the universe ought to behave based on human comfort or everyday intuition. If nature chose to operate through probabilities and waves of potentiality at its deepest levels, then humanity simply had to accept that reality and adjust its thinking accordingly. The Copenhagen interpretation did not offer a comfortable, cozy picture of the cosmos, but it possessed the immense advantage of being flawlessly supported by every single piece of data emerging from real-world laboratories. It worked with absolute stunning precision, even if it left everyone feeling a little bit seasick regarding the stability of existence. To help people visualize the sheer strangeness of this debate, Erwin Schrödinger introduced his legendary and immortal thought experiment involving a cat trapped inside a sealed box. Imagine a completely enclosed, opaque box. Inside this box, you place a living cat alongside a highly dangerous apparatus. This apparatus consists of a tiny radioactive sample, a Geiger counter to detect radiation, a tiny hammer, and a sealed glass vial containing a deadly poisonous gas. The experiment is precisely rigged so that there is exactly a 50% chance that a single atom of the radioactive substance will decay within the span of 1 hour, and an equally perfect 50% chance that it will not decay at all. If the atom happens to decay, the Geiger counter will instantly detect it, triggering a mechanism that releases the hammer to smash the vial, releasing the poison and causing the cat to pass away. If the atom does not decay, the mechanism remains completely idle, and the cat continues to live safely. Now, you close the lid of the box, set a timer for exactly 1 hour, and step away. From the perspective of our everyday common-sense classical world, we know with absolute certainty that during that hour, the cat inside is either entirely alive or it is entirely dead. There are no other logical options. The outcome has already occurred inside the sealed box, and our act of opening the lid after an hour will simply reveal a truth that has already taken place. But according to the strict literal mathematics of the Copenhagen interpretation, the subatomic radioactive atom cannot choose a single state until it is measured. It must exist in a fluid quantum superposition of being both decayed and non-decayed simultaneously. And because the physical life of the cat is directly entangled with the behavior of that atom, the wave function of the entire system must expand to include the cat. Therefore, until the precise moment you open the lid to look inside, the cat is mathematically forced to exist in a surreal superposition of being both alive and dead at the exact same time. It is a ghostly hybrid of two completely contradictory realities, suspended in a cosmic haze of undecided potential. Schrödinger did not design this bizarre scenario because he disliked animals or wanted to promote a belief in zombie cats. In fact, he created it to highlight what he viewed as a massive, glaring conceptual problem in the Copenhagen interpretation when you attempt to scale it up from individual atoms to macroscopic, everyday objects. He was essentially arguing that if the math forces you to conclude that a cat can be simultaneously alive and dead, just because the box is closed, then the interpretation must be missing something fundamental about how reality works. Yet, to the utter amazement of the scientific world, as decades passed and technology advanced, experimenters found ways to put larger and larger systems into real physical superpositions. While we cannot easily isolate a large, warm, furry cat from the messy environment, scientists have successfully put massive molecules, electrical currents, and tiny mechanical mirrors into states where they occupy multiple physical conditions at the exact same time. The math of superposition refuses to break down, no matter how uncomfortable it makes us feel. As you rest quietly in the stillness of the evening, let your mind drift over the sheer depth of this mystery. Think about the physical objects surrounding you in your room right now. The lamp on your nightstand, the book resting on your blanket, the glass of water sitting nearby. In the classical view, those items are rock solid, fixed, and permanently there in exact coordinates, whether you are looking at them or not. But the quantum view suggests a far softer, more fluid reality. It whispers that when you turn your back, close your eyes, and withdraw your awareness from the world, the sharp edges of existence begin to gently blur and spread out into a soft shimmer of possibilities. The universe hesitates, holding its breath in a quiet dance of superpositions, waiting patiently for the exact moment you open your eyes to bring it back into focus. This profound realization completely flips our traditional understanding of the relationship between human awareness and the physical cosmos. For centuries, science operated under the assumption that the universe was a giant, indifferent clockwork machine, and that human beings were merely passive spectators peering in through a cold glass window, observing an objective reality that had absolutely nothing to do with them. But quantum physics, through the voice of the Copenhagen interpretation, shatters that glass window completely. It invites us to step inside the machine, demonstrating that the spectator is actually an active participant in the creation of reality. The choices we make regarding how we observe the world, the exact questions we choose to ask, and the precise measurements we choose to perform, directly shape the physical outcomes that manifest before our eyes. The cosmos is not a finished, static painting hanging on a museum wall. It is an active, ongoing dialogue between the observer and the observed, a fluid tapestry that requires our participation to stitch its final patterns together. This ongoing debate between Einstein's unyielding realism and Bohr's probabilistic quantum world did not end with their passings. It remains one of the most vibrant, fiercely contested battlegrounds in all of modern theoretical physics. Over the decades, alternative interpretations have emerged to challenge the Copenhagen monopoly. Some physicists, embracing the de Broglie-Bohm pilot wave theory, have attempted to rescue Einstein's dream by suggesting that particles do have exact positions, guided along by a real, invisible quantum wave. Others have turned toward the breathtakingly radical many worlds interpretation, which boldly suggests that the wave function never actually collapses at all. Instead, every single time a quantum measurement is made, the entire universe physically splits into multiple parallel branches. In one universe, the radioactive atom decays and the cat passes away. In another parallel reality, the atom remains intact and the cat lives on. Every single quantum possibility is fully realized in its own independent universe, creating an infinite, ever-branching multiverse of existence. It is an absolutely dizzying concept to contemplate, yet it stems directly from taking the smooth, uncollapsed mathematics of Schrödinger's equation with absolute literal seriousness. If you find your mind spinning slightly at the thought of infinite parallel realities branching off with every single subatomic interaction, take a deep, slow breath and find comfort in the fact that even the greatest minds in human history have felt exactly the same way. The quantum world is not meant to feel comfortable or easy to our brains, which evolved to dodge solid rocks and hunt macroscopic animals in a local environment. It is a realm that demands a profound intellectual humility, a willingness to let go of our rigid preconceptions and listen to what the universe is actually telling us about its inner workings, no matter how strange it sounds. And as we continue our slow journey through this cosmic landscape, the mysteries only grow deeper and more beautiful. Because beyond the fluid superpositions of individual particles lies a phenomenon so profoundly strange, so utterly defiant of our basic understanding of space and time, that it made even Albert Einstein recoil in a state of pure, unadulterated disbelief. It is a phenomenon that connects separate particles across vast distances of empty space, creating an unbreakable, instantaneous bond that completely ignores the cosmic speed limit of light. It is a mystery that forces us to question whether the concept of separation itself is nothing more than an illusion. To understand this next mystery deeply, we must explore a concept that Albert Einstein himself found so deeply unsettling that he famously dismissed it as spooky action at a distance. This phenomenon is known to modern science as quantum entanglement. Imagine you have a single physical system that suddenly splits or creates two independent subatomic particles simultaneously. Because of the strict, unyielding laws of conservation in our universe, such as the conservation of angular momentum or electrical charge, the physical properties of these two newborn particles are permanently, inextricably linked together from the very moment of their creation. In the precise language of quantum mechanics, they do not possess individual, independent wave functions anymore. Instead, they share a single, unified, combined wave function that spans across the environment. Let us make this highly abstract concept much more visual and concrete with a simple everyday analogy. Imagine you have a pair of ordinary shoes, a left shoe and a right shoe. You take each shoe and place it into its own separate, identical, secure cardboard box. You mix the two boxes up thoroughly until you have absolutely no idea which box contains which shoe. Now, you keep one box with you here on Earth, and you give the second box to an astronaut who boards a rocket ship and travels millions of miles away to the opposite side of the galaxy. If you decide to open your box here on Earth and look inside, and you discover that you have the left shoe, you instantly and automatically know, with absolute certainty, that the astronaut on the other side of the galaxy must be holding the right shoe inside their box. There is no delay, no hesitation, and no mystery. In our classical, everyday world, this scenario is completely straightforward and entirely free of surprises, because the shoes were always inherently a left shoe and a right shoe from the very beginning. The box did not change them, and your act of looking at your shoe did not physically send a signal across the cosmos to alter the other shoe. The identity of each shoe was fixed and real the entire time it was traveling through space. But when we transition to the quantum scale and look at entangled particles, the Copenhagen interpretation tells us a completely different and far more radical story. According to quantum theory, before you open your box, the particle inside does not possess a fixed identity. It is not a left shoe or a right shoe. Instead, it exists in a fluid quantum superposition, acting simultaneously as both a left shoe and a right shoe at the exact same time. It is a shimmering hybrid of both possibilities. The particle in the astronaut's box across the galaxy is in the exact same undecided state, suspended in a wave of pure potentiality. But the absolute instant you open your box on Earth and perform a measurement, the shared wave function immediately collapses. Your particle instantly chooses to become a left shoe, and in that precise identical microsecond, the entangled particle millions of miles away is instantly forced to collapse as well, instantly transforming into a right shoe to maintain the perfect balance required by the laws of conservation. This is precisely what made Albert Einstein's mind recoil in absolute disbelief. If the two particles were completely undecided before the measurement, how did the distant particle instantly know that its partner on Earth had been observed and had chosen to go left? According to Einstein's own celebrated theory of special relativity, nothing in the physical universe, no signal, no force, no piece of information can ever travel faster than the absolute cosmic speed limit of light. Yet, the collapse of these entangled particles appears to happen instantaneously, completely ignoring the vast distances of empty space separating them. It implies a deep underlying connectivity that operates entirely outside of our familiar concepts of space and time. Einstein was utterly convinced that this instantaneous connection was an outright impossibility. He believed it strongly demonstrated that the quantum theory developed by Bohr and his colleagues was fundamentally flawed and incomplete. In the year 1935, Einstein, along with his brilliant colleagues Boris Podolsky and Nathan Rosen, published a historic paper outlining what would become globally famous as the EPR paradox. In this paper, they argued that because the distant particle instantly reacts with a perfect, predictable property the moment the local particle is measured, that property must have been fixed and real all along, long before any human stepped in to look. They claimed that the particles must carry some form of pre-existing, hidden instructions inside them, like a pair of secret matching notes hidden in the boxes, that predetermined exactly how they would behave when examined. This viewpoint, known as local realism, asserted that physical objects possess real, definite properties, independent of observation, and that interactions must respect the local speed limits of space. For nearly 30 years, this intense debate remained stuck in the realm of pure philosophy. There was no known way to peer inside the particles to see if those hidden variables actually existed, and both the Copenhagen view and Einstein's local realism predicted the exact same practical outcomes in basic experiments. It seemed like an unresolvable argument between two deeply different ways of viewing reality. But then, in the year 1964, a quiet Northern Irish physicist named John Stuart Bell published a breathtakingly brilliant mathematical theorem that completely changed the landscape of science forever. It became known as Bell's theorem. Bell realized that if you were to measure the properties of entangled particles along multiple different angles or axes, rather than just checking a single simple property, you could set up a statistical test. If Einstein's hidden variables were real and the particles carried fixed, predetermined traits all along, the correlations between the measurements could never exceed a strict mathematical limit. This limit became known as Bell's inequality. However, if the quantum world was truly as fluid and interconnected as the Copenhagen interpretation claimed, the particles would exhibit a degree of coordination that would completely shatter that classical limit, producing correlations far stronger than any hidden variable theory could ever possibly allow. Suddenly, a purely philosophical argument had been transformed into a concrete, experimental question that could be physically tested in a laboratory. It took several decades for technology to become precise enough to run these delicate tests cleanly, but during the 1970s, 1980s, and onward, pioneering experimental physicists began to build the necessary machines. They generated pairs of entangled photons and fired them in opposite directions down long tubes, measuring their polarization angles at the very last possible microsecond to ensure no classical signal could travel between them in time. And when the final data came pouring out of the computers, the verdict was absolute and unambiguous. Einstein's inequality was completely violated. The correlations between the particles were far too strong to be explained by any hidden variables or pre-existing matching notes. The quantum predictions were proven to be flawlessly correct. The universe had spoken, and it had declared that local realism is completely false. The particles truly do remain undecided until they are observed, and they maintain an unbreakable, instantaneous coordination across space that completely defies our everyday understanding of isolation and distance. This monumental revelation completely changes how we must view the structural nature of space itself. It strongly implies that at a deep, fundamental level, the universe is non-local. Separate objects that appear to be completely isolated from one another across vast expanses of empty space are not truly separate at all. They remain quietly, invisibly woven together into a single, continuous cosmic tapestry. The concept of separation, which feels so incredibly real and absolute to us in our daily macroscopic lives, appears to be nothing more than a superficial illusion, born of our limited human scale. As you lie still in the quiet warmth of your room tonight, let yourself ponder the sheer, breathtaking beauty of this reality. Every single particle of matter making up your body, the air you are breathing, and the distant stars burning in the night sky was once tightly packed together in a single, unimaginably dense point at the very beginning of time during the Big Bang. In a very real, physical sense, the entire cosmos shares a common origin. And if particles become permanently entangled when they interact, it means the entire universe is a vast, shimmering web of quantum connections. A beautifully synchronized dance where everything is quietly whispering to everything else across the dark, silent gulfs of space. This profound insight has moved far beyond the realm of theoretical physics and is actively driving a modern technological revolution. Scientists and engineers around the world are currently utilizing the power of quantum entanglement to build a completely new generation of tools. It forms the absolute foundation of quantum cryptography, a method of secure communication that uses entangled photons to send information. Because any attempt by a spy to intercept or look at the photons instantly collapses their shared wave function, the communication system can automatically detect the eavesdropper immediately, making the encryption completely unhackable by the laws of physics. Entanglement is also the vital fuel driving the development of quantum computers. While ordinary computers process information using classical bits that must be strictly a 0 or a 1, quantum computers utilize qubits that can exist in a fluid superposition of both states simultaneously. By entangling these qubits together, the computer can explore an astronomical number of possible solutions to a complex problem all at once, performing calculations in a matter of seconds that would take a traditional supercomputer thousands of years to solve. We are actively learning to harness the very spookiness that once terrified Einstein to reshape the future of human technology. Yet, even as we build these incredible machines, the deep mystery of why the universe operates this way remains completely wide open. How does the wave function collapse happen? Where does the line between the quantum world and the classical world truly sit? This brings us directly to a beautifully elegant concept known as quantum decoherence, which helps explain why we do not see tables, chairs, or human beings existing in ghostly superpositions in our daily lives. Think about a single, isolated electron traveling through the empty vacuum of space. It is incredibly small, light, and untouched by its environment, allowing it to easily maintain its fluid wave function and explore multiple paths simultaneously. But now, think about a macroscopic object, like a single grain of sand or a ceramic teacup. That object is composed of countless billions of trillions of individual atoms, and it is constantly being bombarded by its surroundings, is constantly colliding with air molecules, absorbing and emitting thermal infrared radiation, and rubbing against other physical surfaces. Each and every one of those countless microscopic interactions acts as a tiny, informal quantum measurement. The environment is constantly spying on the object, leaking its quantum information out into the surrounding world. This constant, unyielding interaction with the environment causes the object's complex quantum coherence, its ability to maintain a clean superposition of states, to decay away almost instantaneously. The fluid wave function does not need a human scientist with a PhD to step in with a fancy laboratory detector to collapse. The chaotic environment itself is constantly performing the measurement every single fraction of a second. This incredibly rapid process of quantum information dissolving into the surroundings is what physicists call decoherence. It acts as the natural bridge that seamlessly connects the fuzzy, shimmering quantum realm to the sharp, rock-solid, classical reality that we experience with our senses. It explains why the microscopic building blocks of the universe can be completely uncertain and wave-like, while the macroscopic structures they build remain firmly, reliably pinned in place. As you settle deeper into the quiet comfort of your bed, let your awareness rest on this gentle, reassuring process. The entire world around you is constantly holding itself together through this unyielding, silent dialogue. The air brushing against your skin, the weight of the blankets resting on your body, the soft surface of the pillow supporting your head. All of these things are continuously interacting, constantly sharing information, and quietly keeping one another firmly anchored in reality. You do not have to worry about the room around you dissolving into a cloud of fluid possibilities while you sleep tonight. The cosmos is taking care of itself, beautifully and reliably stitching the fabric of existence together with every passing microsecond, ensuring that when you wake up and open your eyes tomorrow morning, the world will be waiting for you exactly as you left it. Current part, being, written, part 4, total parts, planned, 8 narrative window, from the 60 minutes mark to the 80 minutes mark of the original timeline. Target word count for this part, 2,000, 3,000 words. To fully appreciate the strange, unyielding nature of the subatomic landscape, we must look closely at a concept that fundamentally redefines our understanding of nothingness itself. In our traditional, everyday macroscopic experience, the concept of a vacuum implies absolute emptiness. If you take a solid glass container and completely pump out every single atom of gas, every stray molecule, and every single ripple of thermal heat, you expect to be left with a perfectly still, completely inactive void. Common sense insists that nothingness should remain quietly nothing. But when we apply the strict mathematical principles of quantum mechanics to this empty space, we discover a reality that is breathtakingly alive. According to the laws of quantum field theory, What we call empty space is not actually empty at all. It is the quantum vacuum, and it is a vibrant, continuously fluctuating field of energy. Because of the built-in, unyielding constraints of Heisenberg's uncertainty principle, a quantum field can never settle down into a state of absolute zero energy. If it were to become completely still and empty, its value and its rate of change would both be precisely defined at the exact same moment. As we have firmly established, the universe explicitly forbids that level of absolute certainty. Therefore, even in the deepest, coldest depths of intergalactic space, far removed from the warmth of any burning star, the vacuum must constantly jitter with a baseline, unstoppable energy. This unceasing activity manifests as a surreal phenomenon known as vacuum fluctuations. Out of the absolute emptiness of the void, pairs of virtual particles are constantly, spontaneously leaping into physical existence. A tiny electron and its antimatter twin, a positron, will suddenly materialize from nothingness, flash into existence for a minuscule fraction of a second, and then instantly collide with one another and annihilate back into the background energy of the universe. These particles are not permanent fixtures of matter. They are ghostly borrowers of energy, utilizing a tiny loophole in the uncertainty principle that allows a massive amount of energy to be borrowed from the cosmos, as long as it is paid back almost instantaneously. It sounds like a mathematical fiction, a clever accounting trick that physicists invented on paper to make their equations balance out. Yet, these virtual particles leave behind real, completely measurable signatures in our physical world. When scientists meticulously correct their complex atomic calculations to include the physical influence of these vacuum fluctuations, they find a stunning real-world validation. A famous historical example is the Lamb shift, a tiny, subtle shift in the energy levels of the hydrogen atom's orbiting electron. When physicists measured this tiny shift in the laboratory, they found that it matched the theoretical calculations that included vacuum fluctuations with absolutely breathtaking, flawless precision. The mathematics might sound wild, but the physical results are as solid as rock. In a very profound and literal sense, the quantum vacuum stands as the most fundamental, foundational field in the entire cosmos. Every other physical field that we know of, whether it is the electromagnetic field carrying light, the gravitational field curving space-time, or the nuclear forces holding the cores of atoms together, must exist and operate directly within this vibrating baseline. They ripple, hum, and dance against its background like musical instruments playing a complex melody on top of a deep, resonant bassline that never stops sounding. Because of this, many modern theoretical physicists strongly suspect that the vacuum holds the ultimate clues to the deepest, most elusive truths of our universe. They wonder if this unceasing background activity could be the primal source of all physical structure in the cosmos, perhaps holding the hidden keys to a unified theory of quantum gravity, or even containing the blueprint for the origin of space and time themselves. These remain some of the biggest open questions in modern science. But one thing has been made completely undeniable. The vacuum is not a passive, dead backdrop. It is active, highly structured, and filled to the absolute brim with pure potential. It is a deeply humbling concept to sit with in the quiet stillness of the evening. Nothingness is never truly nothing. Even in the absolute appearance of perfect stillness, the universe is teeming with hidden, microscopic activity. In the brief pauses between moments, in the microscopic gaps separating individual particles of matter, and in the immense silent expanses that stretch between distant stars, something is always actively happening. We do not live out our lives on a cold, quiet, static stage. We live on a stage that constantly murmurs, vibrates, and breathes beneath our feet. As we absorb the reality of this shimmering canvas, we must also confront how these strange quantum behaviors alter our foundational views on causality and determination. If we look closely at how a quantum system evolves, we see that it resists every single effort to explain it using the cozy, familiar terms of our daily lives. We are deeply accustomed to a world where an object follows a single, clear, highly predictable path through space and time. When an ordinary baseball leaves an outfielder's hand, it travels through the air along a definitive trajectory. You can calculate its exact landing spot before it ever gets there. Even if you flip a coin into the air and you do not personally know whether it will land on heads or tails until it hits the ground, we know that it is definitively one or the other during its entire flight. The outcome is simply hidden from your eyes due to a lack of data. Quantum systems completely shatter that way of thinking. In the quantum realm, if you flip a subatomic coin, it does not secretly occupy a single side while you are looking away. Instead, it genuinely enters a physical state of quantum superposition, a beautifully weighted combination of both heads and tails simultaneously. It is not merely undecided in its mind, nor is it switching back and forth between the two states at high speed. It physically exists as both possibilities at once, spreading its identity across a shimmer of choices, and the very instant an observer steps in to extract information from that system, the moment a measurement is conducted, that spread out cloud of possibilities suddenly collapses down to a single point. The system is forced to pick a side. One solitary possibility instantly hardens into concrete reality, while all the other potential stories vanish into nothingness as if they never existed. But this raises a deeply challenging, highly controversial question that has puzzled the scientific community for a century. What exactly qualifies as a formal measurement? Does it strictly require the presence of a conscious human being looking through a microscope? Does it happen when a mechanical detector clicks in a laboratory? Or does it occur the moment the quantum particle bumps into any random piece of the surrounding environment? Different interpretations of quantum mechanics offer vastly different answers to this profound riddle, and this lingering ambiguity is precisely why Schrödinger's cat continues to capture so much public attention and debate. The scenario forces us to confront the reality that quantum theory, while being breathtakingly successful at predicting statistical outcomes in our experiments, remains oddly, hauntingly silent about what is actually occurring behind the scenes during the quiet spaces between our measurements. To help navigate this conceptual haze, we must journey back to the historical birthplace of these radical ideas. If quantum physics could be said to possess a physical hometown, it would undoubtedly be the city of Copenhagen. This is not due to its beautiful scenery or its charming supply of windmills and bicycles, but because it was within the walls of Niels Bohr's Institute that some of the most surreal and challenging ideas in modern science were first seriously debated, fought over, and quietly integrated into mainstream physics. Standing at the absolute centre of this intellectual movement was Niels Bohr himself. Bohr was a man of immense patience, a gentle demeanour, and a famous fondness for constructing long, exceptionally complex sentences as he wrestled with deep thoughts. Alongside his brilliant colleagues, Bohr meticulously shaped a cohesive perspective on the quantum world that would globally become known as the Copenhagen interpretation. The core foundational premise of the Copenhagen interpretation is deceptively simple, yet its implications are entirely revolutionary. It boldly asserts that a quantum system does not possess definite objective physical properties during the periods when it is not being actively measured. An electron does not occupy a fixed, real coordinate in space as it circles a nucleus. A photon does not possess a definitive orientation or polarization as it glides through the dark. A particle does not commit itself to a single, concrete state of existence until an external observation explicitly forces it to make a choice. Before that definitive moment of measurement, reality is a fluid, spread-out cloud of pure possibilities, a probability wave mathematically governed by the Schrödinger equation. The act of measurement does not simply pull back a curtain to reveal a pre-existing truth that was quietly waiting to be discovered. The act of measurement actively creates the physical outcome itself. In other words, the Copenhagen view delivers a stunning blow to traditional realism by suggesting that reality is not quite real until we ask it to be. It is a stunningly bold claim, the exact kind of radical statement that makes philosophers sit up in deep contemplation and forces physicists to reach for another cup of coffee. But Bohr and his circle were definitely not trying to inject artificial mystery into the cosmos just for the sake of being provocative. They were driven to this radical position because they were trying to make sense of the hard, undeniable data emerging from their laboratory experiments. Every single time they tried to treat subatomic particles like tiny, reliable, classical billiard balls that possessed fixed trajectories and real properties when unobserved, the underlying mathematics completely fell apart into nonsense. But the moment they treated those particles as fluid waves of probability that only resolved themselves into a single outcome upon the explicit act of measurement, everything clicked together with perfect harmony. The math worked flawlessly. In this Copenhagen view, the mathematical wave function is not a literal physical object that you can touch or see. It does not describe a particle's actual concrete position or its real-time momentum. Instead, it serves as a highly sophisticated mathematical catalogue that encodes absolutely everything that can possibly be known about the system. It is a detailed ledger of potential choices, not a literal map of what currently exists. This leads directly to one of the most central, unyielding claims of the Copenhagen philosophy. Asking questions about a physical system's state before a measurement has occurred is completely and utterly meaningless. Asking exactly where an electron was located before you turned on your laboratory detector does not make any logical sense, because the very concept of where only gains a valid meaning after the measurement has taken place. Reality is not a static, objective painting that sits quietly behind a curtain, waiting for us to step up and peel the cloth back. It is a fluid tapestry that violently snaps into sharp focus the exact microsecond you choose to look at it. The subatomic particle wasn't secretly hiding its true nature from our eyes. It simply did not possess a definitive nature yet. Understandably, this deeply fluid view of existence left many traditional scientists feeling profoundly unsatisfied and deeply uncomfortable. Albert Einstein, most famously of all, was completely uneasy with this picture of the world. He desperately wanted a universe that existed objectively and independently, completely separate from whether a human being or a machine was actively observing it. He believed with every fibre of his being in an underlying reality that was fundamentally objective, stable, and deterministic, even if those details were currently hidden from our primitive view. To Einstein's realism-centered mind, the claims of the Copenhagen interpretation sounded completely absurd, like looking at someone and telling them that the moon up in the night sky literally ceases to exist the moment everyone turns their back and stops looking at it. Bohr, however, strongly disagreed with Einstein's complaints, but he did not try to counter them by offering a grand, elaborate metaphysical theory. Instead, Bohr calmly embraced a pragmatic, highly practical ambiguity. His firm position was that quantum theory does not describe what nature inherently is in its secret heart. Rather, it describes what we can explicitly say about nature based on our experiments. The ultimate role of science, in this modern view, is not to discover some hidden, objective truth that exists independent of us, but to describe the concrete outcomes of real-world experiments as precisely and reliably as humanly possible. If that perspective strikes you as a little bit cold or unsatisfying, you are certainly not alone in that feeling. Throughout the history of science, the Copenhagen interpretation has been frequently accused of being more of a practical medical prescription than a true, deep description of reality. It tells you exactly how to utilize the mathematical equations, and it tells you precisely what the experimental outcomes will be, but it completely refuses to tell you what is actually happening behind the scenes while the box remains closed. This pragmatic refusal gave rise to a legendary, infamous phrase among modern physicists: shut up and calculate. While this specific quote did not originate from Bohr himself, it perfectly captures the underlying mood of countless working scientists throughout the 20th century and into the modern era. The underlying sentiment is simple: stop stressing over the deep metaphysical and philosophical implications of the theory and just use the mathematics. The theory works. It yields perfectly accurate predictions every single time. Why shouldn't that be enough? And to be completely fair to the pragmatists, the Copenhagen approach has proven to be an incredibly successful way to do science. It has stood for decades as the default mainstream interpretation taught in nearly every physics textbook, laboratory, and university classroom across the globe. It forms the absolute scientific foundation that underpins the engineering of modern semiconductors. the creation of advanced lasers, and the development of cutting-edge quantum computers. It has never once failed a single physical experiment in over a century of testing. For the vast majority of working scientists, that flawless track record completely outweighs any lingering philosophical discomfort they might feel. Yet, despite its practical dominance, the deep discomfort completely refuses to vanish. If reality truly only becomes concrete and real when it is measured, what does that say about the state of our universe during the vast eons of time before any observers ever existed? Did absolutely nothing in the cosmos possess definite physical properties before conscious life finally arrived on the stage? Was the early universe suspended in a ghostly, undecided animation for billions of years, waiting patiently for some primitive eye to finally look at it and force it to collapse into a real history? Most modern physicists would answer that question with a gentle but definitive no. The Copenhagen interpretation does not actually require a conscious, living human observer to function. It merely requires a physical interaction between a quantum particle and a larger classical system, such as a mechanical measuring device or the surrounding environment. In this context, observation is not an act of mystical consciousness. It is simply a physical process of extracting information from a quantum system in a way that forces it to pick a definitive side. As we reflect on these deep concepts in the quiet comfort of the night, it is incredible to see how these philosophical debates have completely transformed our world. What began as a quiet fix for a black body radiation problem in 1900 has bloomed into a magnificent, shimmering tapestry of understanding that guides our modern civilization. The universe whispers its secrets to us in a language of waves and probabilities, inviting us to accept its beautiful mysteries rather than forcing it into our rigid classical boxes. If this is the case, it forces us to continuously explore further questions. What exactly qualifies as a formal measurement? Does it require a massive chunk of metal, a complex configuration of circuits, or does the universe simply resolve its own uncertainties through the silent, unceasing interactions of its fundamental parts? As we look closer at these profound mysteries, we find that the answers might not be hidden in a completely new set of particles, but rather in a radical reorganization of how we conceptualize the entire subatomic landscape. To truly appreciate this cosmic architecture, we must transition our focus away from the behavior of individual isolated particles and step boldly into the magnificent, unified framework of quantum field theory. In our traditional ways of imagining the subatomic world, we very often picture an electron as a tiny, hard, reliably solid sphere that zips through empty space like a microscopic planet orbiting a heavy sun. We think of light as a stream of individual photon bullets fired through the void. But as physics pushed deeper into the heart of reality, this particle-centric model began to create immense conceptual bottlenecks. It couldn't fully explain how forces traveled through empty space or how particles could be spontaneously created and destroyed out of nothingness during high-energy collisions. To solve these deep riddles, theoretical physicists had to completely invert their perspective. They realized that particles are not the primary citizens of the universe. The true foundational bedrock of existence is the quantum field. Imagine an infinite, invisible ocean that stretches out continuously through every single cubic centimeter of the entire universe, filling all of empty space from the center of your room to the most distant intergalactic voids. This ocean is completely uniform, perfectly smooth, and quiet when it is in its lowest energy state. This is what we call a quantum field. Now imagine that something suddenly perturbs this ocean, causing a ripple or a small localized wave to travel through the water. In the elegant language of quantum field theory, that tiny ripple, that specific localized packet of vibrating energy, is exactly what human beings perceive with their instruments as a physical particle. There is a unique, dedicated field for every single fundamental element known to science. The electron is not an independent object traveling through space. It is a localized, vibrating ripple in the vast universal electron field. A photon is nothing more than a localized wave traveling through the all-permeating electromagnetic field. There are up quark fields, down quark fields, neutrino fields, and Higgs fields, all layered on top of one another like sheets of fine silk woven together into a single, incredibly complex cosmic fabric. If you alter the vibration of the field just slightly, the characteristics of the particle change. Twist the frequency of an electromagnetic ripple in one direction, and you create visible light that fills a room. Shift it slightly differently, and you generate invisible microwaves or high-energy X-rays. Yet, beneath all of these diverse manifestations, it is all just the same fundamental fields dancing in different ways. This profound shift in perspective completely clarifies how particles are able to interact across vast distances. When two electrons push away from each other, due to their matching electrical charges, they are not directly colliding like classical billiard balls. Instead, the ripple in the first electron field creates a corresponding disturbance in the surrounding electromagnetic field, which then travels outward and pushes against the ripple in the second electron field. It is a continuous, elegant ballet of overlapping waves influencing waves. The old familiar concept of a solid, independent particle is ultimately a highly useful fiction, a simplified, convenient label that humans use to describe the localized, discrete behaviors of these underlying fields. The field itself is the only thing that is truly fundamental, permanent, and real. As you lie still in the deep, quiet dark of your room tonight, let your mind completely let go of the idea that you are surrounded by cold, empty space. There is no such thing as true emptiness anywhere in the cosmos. Your body is currently resting within a deeply structured, intricately woven matrix of universal fields, the atoms making up your skin, the air swirling softly through your lungs, and the silent moonlight filtering through your window are all beautifully synchronized ripples dancing in unison across these invisible cosmic oceans. We are not isolated, lonely wanderers moving through a barren, dead void. We are an integral, inseparable part of a living, breathing, continuously vibrating tapestry of energy that connects absolutely everything in existence. If the universe came with an official handbook, the standard model of particle physics would stand as its definitive master ingredient list. It is a shockingly compact, beautifully organized recipe that catalogues the absolute building blocks of our physical reality. Despite a few minor missing pieces that scientists are still actively hunting for, this framework stands proudly as one of the most wildly successful, rigorously verified theories in the entire history of human science. It explains with absolute mathematical precision how the microscopic world holds itself together, how elements interact, and why the physical world behaves with such remarkable stability. Let us gently introduce the fascinating cast of characters that populate this subatomic world. At the absolute foundation of the standard model are the elementary particles, units of matter and force that, as far as modern technology can tell, possess absolutely no internal structure and cannot be broken down into anything smaller. They are the irreducible pieces of our reality, woven together by the invisible threads of their corresponding quantum fields. The standard model beautifully organizes these fundamental actors into three distinct, elegant families: the quarks, the leptons, and the bosons. The first family, known as the quarks, represents the heavy, incredibly tough building blocks that form the solid cores of all atomic nuclei. In a brilliant display of scientific whimsy, physicists decided to categorize these quarks into 6 unique types, which they officially call flavors: up, down, charm, strange, top, and bottom. While theoretical physicists are capable of executing the most staggeringly precise, mind-boggling mathematics imaginable, their conventions for naming things are often delightfully chaotic. The up and down quarks are the lightest, most stable, and by far the most abundant members of this family. A standard proton, which sits at the center of an atom, is constructed from a tight trio consisting of 2 up quarks and 1 down quark. A neutron, its electrically neutral partner, is built from 2 down quarks and 1 up quark. This means that absolutely everything you can see, touch, or interact with in your daily life, the solid wood of your bed, the water in your glass, and the very bones in your body, is constructed almost entirely from up and down quarks, alongside a sprinkling of electrons. The other four flavors of quarks, charm, strange, top, and bottom, are significantly heavier, highly unstable, and exceptionally rare in the modern cosmos. They act as the brilliant, short-lived guest stars of the subatomic world, appearing only in high-energy environments like massive particle accelerators or violent cosmic ray collisions before instantly decaying back into simple energy. The second great family of the Standard Model consists of the leptons. The most famous and familiar member of this group is the electron, an indispensable particle that spends its existence buzzing around atomic nuclei, generating electrical currents, creating chemical bonds, and generally making the existence of life possible. But just like the quarks, the electron has its own set of heavier, more exotic cousins. There is the muon, which behaves exactly like a heavy, unstable electron, and the tau, which is even heavier still. These heavy leptons disappear almost as quickly as they are created, but they leave unmistakable, highly distinct traces in our specialized laboratory detectors. Fascinatingly, each of these three charged leptons travels through the universe with a ghostly, completely neutral companion known as a neutrino. There are three distinct flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino, and they are unimaginably light, incredibly fast, and staggeringly aloof. Because they possess no electrical charge and practically zero mass, neutrinos are the ultimate introverts of the particle world, completely refusing to interact with normal matter in any meaningful way. Right now, at this very microsecond, billions of neutrinos streaming out from the nuclear furnace of the sun are passing completely through your body, through your mattress, and straight through the solid core of the Earth without hitting a single atom or leaving a single trace of their passage. When we sum them up, we find 6 unique quarks and 6 unique leptons, beautifully arranged in 3 neat, balanced generations of matter. This gives us 12 fundamental matter particles that form the physical substance of the universe. But matter on its own is completely static and inert. It cannot build a dynamic universe without the presence of forces. We need strict rules and active messengers to govern how these matter particles pull, push, and bind to one another. This vital role is fulfilled by the third family of the Standard Model, the bosons. Bosons are the official force carriers of the universe, acting as quantum handshakes or microscopic sticky notes passed back and forth between matter particles to tell them exactly how to behave. For example, the electromagnetic force, which governs light, magnetism, and static electricity, is carried exclusively by the photon. The photon is completely massless, travels at the absolute speed limit of the cosmos, and mediates every single interaction between electrically charged particles. When you feel the warmth of a fire or see the glow of a screen, you are experiencing the direct work of boson messengers delivering energy to the atoms in your eyes and skin. By mapping these 12 matter particles and their corresponding force carriers, the Standard Model builds a complete, breathtakingly precise framework of the subatomic realm. It shows us that the chaotic diversity of our macroscopic world is built upon a foundation of profound symmetry, order, and simplicity. It allows us to calculate the properties of matter to an astonishing number of decimal places, proving time and again that the universe operates according to deeply elegant mathematical harmonies. As you rest quietly in the deepening silence of the night, allow yourself to marvel at the sheer perfection of this cosmic machinery. Every single breath you take, every soft heartbeat pulsing in your chest, and every fleeting thought drifting through your mind is orchestrating a flawless, hyper-precise symphony of quarks, leptons, and bosons interacting across invisible fields. You are not a separate observer looking in on the universe from the outside. You are a beautifully organized, highly coherent gathering of these fundamental pieces, temporarily brought together to experience this brief moment of consciousness in a vast and shimmering reality. The cosmos is not far away. It is humming softly inside you, holding you safely in its embrace as you gently surrender to sleep. To completely comprehend how these distinct pieces of force and matter communicate with one another, we must introduce the other essential force carriers that inhabit the Standard Model. Alongside the familiar photon, which manages all electromagnetic interactions, there are massive particle messengers that operate over incredibly short distances. When we look deep inside the nucleus of an atom, we discover the weak nuclear force, which is uniquely responsible for radioactive decay and helps power the essential nuclear reactions that make the sun burn. This short-range force is mediated by three heavy, highly specialized bosons: the W+, the W-, and the Z boson. Unlike the completely massless photon, these weak force carriers are exceptionally heavy and dense, possessing a massive amount of physical weight that severely restricts their range of influence. They can only travel across a tiny fraction of an atomic nucleus before decaying away, acting like incredibly heavy packages that require a massive amount of energetic effort to throw even a tiny distance. Next, we must examine the strong nuclear force, which acts as the ultimate superglue of the subatomic universe. This force is responsible for holding quarks together inside protons and neutrons, completely overcoming the massive electrical repulsion that tries to push matching charges apart. The dedicated messengers of this incredibly powerful force are called gluons, and they operate in a completely unique way. While photons carry electrical charge but do not interact with other photons directly, gluons actually carry the very force they transmit, which physicists call color charge. This means that as gluons travel back and forth between quarks, they pull and attract one another, creating an unbreakable, highly elastic bond that gets stronger and tighter the further you attempt to pull the quarks apart. It behaves exactly like a thick rubber band. When the quarks are close together, they move with total freedom. But if you try to separate them, the tension skyrockets instantly, trapping them permanently inside their nuclear home. Finally, we arrive at the most famous and elusive member of the boson family, the legendary Higgs boson. For decades, this particle existed exclusively as a brilliant theoretical concept, first proposed in the 1960s to solve a massive, glaring flaw in the Standard Model equations. The core problem was that the basic mathematical formulas required all fundamental particles to be completely massless, traveling at the absolute speed of light forever. But our real-world experience demonstrates that electrons, quarks, and weak bosons undeniably possess real, physical mass. To fix this, scientists proposed that the entire universe is filled with an invisible, all-permeating field known as the Higgs field. As elementary particles travel through this field, they interact with it, experiencing a form of cosmic drag that manifests to our instruments as physical mass. Particles that interact heavily with the field gain a massive amount of weight, while particles like photons pass right through without touching it, remaining completely massless. In the year 2012, after decades of anticipation and the construction of the most massive scientific machine ever built by humanity, the Large Hadron Collider at CERN, experimental physicists finally discovered the real physical excitation of this field, the Higgs boson particle itself. This historical discovery was the final definitive crown jewel of the Standard Model, completing the master ingredient list and proving that our theoretical understanding of how matter gains its physical substance was completely correct. It showed that mass is not an inherent, basic trait that particles simply possess on their own. Instead, mass is an active, ongoing property generated by a continuous, silent interaction with an invisible field that blankets the entire cosmos. As you rest quietly in the stillness of the night, let your mind reflect on the incredible journey humanity took to uncover this orderly, subatomic family. We peered into the deepest foundations of matter, breaking down the entire visible universe into a handful of irreducible quarks, leptons, and bosons. It is a world of absolute mathematical precision, where every interaction is strictly governed by field values and force exchanges, creating a beautiful framework of order that allows our macroscopic reality to exist safely. Yet, even with the immense historic success of the Standard Model, the story of quantum physics is far from completely finished. The deeper we look into the calculations, the more we realize that this neat family portrait is surrounded by immense looming shadows of mystery that continue to challenge our finest minds. The absolute greatest crisis facing modern theoretical physics is the total, stubborn refusal of the universe's two most successful theories to speak to one another. On one hand, we have quantum mechanics and the Standard Model, which describe the ultra-small world of fields and particles with flawless, staggering precision. On the other hand, we have Albert Einstein's magnificent theory of general relativity, which describes the macroscopic cosmos, the motion of planets, the behavior of galaxies, and the grand structure of space and time themselves. General relativity explains gravity not as a traditional force carried by particles, but as a smooth, continuous geometric curving of the fabric of space-time itself. A heavy object like a star warps the canvas around it, causing smaller objects to naturally slide toward it along curved paths. When you attempt to combine these two brilliant frameworks into a single unified mathematical equation, everything instantly collapses into absolute chaos and mathematical madness. If you take the smooth, continuous, elegant geometric canvas of general relativity and try to shrink it down to the microscopic quantum scale, you run directly into the violent, unceasing fluctuations of the uncertainty principle. At that ultra-small scale, the fabric of space and time completely stops being a smooth, predictable canvas. It becomes a violent, wildly churning, chaotic froth that physicists call quantum foam. In this microenvironment, the concepts of up, down, before, and after lose all meaning, and the mathematics of relativity completely chokes on the random fluctuations, spitting out answers of infinite energy and infinite probability that are totally disconnected from reality. For nearly a century, the absolute smartest minds on Earth have wrestled desperately to bridge this immense conceptual chasm. They are hunting for a elusive theory of quantum gravity, a single, master framework that can seamlessly describe both the violent jitters of the electron and the grand, smooth curves of a black hole without breaking down into nonsense. This grand quest has given rise to some of the most radical, breathtakingly imaginative mathematical frameworks in human history. The most famous of these attempts is string theory, which boldly suggests that if we could zoom in unimaginably close, past the scale of quarks and leptons, we would discover that particles are not dots or ripples in a field at all. Instead, they are tiny, vibrating, one-dimensional loops of pure energy called strings. According to string theory, just as the different vibrational frequencies of a single violin string can produce entirely different musical notes, the different vibrational modes of these cosmic strings generate all the different particles and forces in the Standard Model. A string vibrating at one frequency manifests to our eyes as an up quark. A string vibrating at a different frequency becomes an electron, and a string vibrating in a completely unique mode becomes the graviton, the hypothetical, long-sought boson messenger of gravity. To make the complex mathematics of these vibrating strings work out cleanly without creating logical paradoxes, the theory requires the universe to possess far more than our familiar 3 dimensions of space and 1 dimension of time. It demands the existence of 10, 11, or even 26 independent physical dimensions, most of which are tightly curled up and hidden away at scales far too small for human instruments to ever detect. It is a dizzying, utterly mind-boggling picture of reality that sounds far more like an elaborate piece of science fiction than a proper branch of material physics. Yet it stands as a testament to just how far humanity is willing to push the boundaries of thought to find a sense of ultimate unity in the cosmos. Whether string theory represents the absolute truth of our universe remains a deeply open, fiercely debated question, primarily because these strings are so unimaginably tiny that building a particle accelerator, powerful enough to see them directly, would require a machine the size of our entire galaxy. Without direct experimental confirmation, it remains a beautiful, mathematically elegant dream, a brilliant whisper of what might be, waiting for a future generation to unlock its secrets. As you lie perfectly comfortable in the deepening quiet of your room, let yourself appreciate the profound beauty of this ongoing scientific struggle. The very fact that our universe contains these deep, unresolved contradictions is not a failure of human intelligence. It is a stunning reminder of just how vast, rich, and wonderfully mysterious reality truly is. We are part of a cosmos that refuses to be easily summarized or neatly tucked into a single human textbook. It keeps some of its deepest secrets hidden away in the violent froth of quantum foam and the curled-up folds of hidden dimensions, teasing us with hints of an ultimate harmony while reminding us to maintain a deep intellectual humility. You do not need to solve the great unification puzzle tonight to feel perfectly at home within this grand design. The mystery is a beautiful feature of our existence, a quiet invitation to remain curious, and a reassurance that there will always be more to discover when tomorrow comes. But now comes the part where we slow down and breathe a little. Quantum computers are not going to replace your laptop anytime soon. They are specialized tools, not general-purpose devices. For tasks like browsing the web or editing a video, your classical computer remains the reigning champion. In fact, building and running a quantum computer is hard. Qubits are incredibly delicate. They can be disrupted by tiny vibrations, fluctuations in temperature, even stray magnetic fields. Maintaining a qubit's coherence, its ability to stay in superposition and entanglement, requires extreme care. Many systems must be cooled to temperatures near absolute zero. That's colder than deep space. And then there's error correction. In classical computers, if a bit flips unexpectedly, it's fairly easy to detect and fix. In quantum systems, it's much trickier. You can't simply copy a qubit state without disturbing it, thanks to the no-cloning theorem. So, researchers have had to invent clever schemes using many physical qubits to protect one logical qubit. It's like wrapping your whispering poet in layers of soundproof insulation so they can keep reciting without interference. Despite these challenges, progress has been impressive. Companies and research labs have built quantum computers with tens to hundreds of qubits. Some have demonstrated quantum supremacy, performing tasks that would take a classical computer an impractical amount of time. Others are developing systems that could revolutionize field after field, turning theoretical dreams into industrial realities. As we look beyond the silicon walls of computers, we find that nature itself might have beaten us to the punch, utilizing these exact same subatomic tricks inside living tissue. This realization marks the birth of a fascinating new discipline known as quantum biology. For a very long time, scientists firmly believed that the warm, wet, and incredibly chaotic environments of living cells would completely destroy any delicate quantum states before they could do anything useful. They assumed that subatomic weirdness was strictly confined to pristine physics laboratories, cooled down to near absolute zero. But life is remarkably stubborn, and over billions of years of evolution, it appears to have found clever ways to harness the quantum world to maximize its own efficiency. The most stunning example of this can be found in the everyday miracle of photosynthesis. When a photon of sunlight strikes a leaf, it transfers its energy to a specialized light harvesting molecule. That energy must then travel across a dense network of proteins to reach a central reaction center, where it can be converted into chemical fuel. In a purely classical world, that packet of energy would have to take a random, chaotic path, bouncing around aimlessly from one molecule to the next like a ball in a pinball machine, losing a massive amount of energy as heat along the way. Instead, experimental data suggests that the energy enters a state of quantum superposition, traveling along every single available path through the protein matrix simultaneously. It explores the entire molecular landscape at once, automatically finding the most efficient, shortest route to the reaction center with near-perfect efficiency. Plants are essentially operating tiny biological quantum processors at room temperature to capture the energy of the sun. But the wonders of quantum biology do not stop with green leaves. Scientists have also turned their attention to the skies, trying to solve the long-standing mystery of how migratory birds are able to navigate across thousands of miles of open ocean with pinpoint accuracy. European robins, for instance, possess an extraordinary internal compass that allows them to perceive the incredibly weak magnetic field of the Earth. Researchers have discovered that this ability is linked to a specialized protein called cryptochrome located inside the bird's eyes. When blue light enters the eye, it strikes this protein and triggers a chemical reaction that creates a pair of entangled electrons. Because these electrons are intimately linked through entanglement, their delicate spin states are exceptionally sensitive to the angle of the Earth's magnetic field lines. As the bird looks around, the shifting magnetic field alters the chemical behavior of these entangled pairs, effectively creating patterns of light and shadow across the bird's field of vision. The bird is literally seeing the invisible magnetic grid of our planet woven directly into its visual reality. Even our own human senses might be deeply connected to these subatomic phenomena. Consider the way your nose decodes the invisible world of molecules swirling through the air around you. The traditional theory of olfaction states that your sense of smell works like a lock and key, where a scent molecule must physically fit into a matching receptor shape inside your nose to trigger a signal to your brain. But this shape-based theory has several strange gaps. Some molecules with identical shapes smell completely different, while other molecules with entirely different structures smell exactly the same. To resolve this, a radical new quantum theory suggests that when a scent molecule binds to a receptor, electrons in the receptor might tunnel through the molecule. The likelihood of this tunneling depends entirely on the molecule's unique internal vibrational frequency. If true, it would mean that part of your sense of smell involves quantum tunneling, the same mind-boggling trick that lets particles pass through seemingly solid barriers in nuclear fusion is happening inside your nostrils. Your nose might be sniffing in stereo, both structurally and vibrationally, using quantum mechanics to help decode the invisible world of molecules. Again, the idea is controversial, but experiments have shown that people and even fruit flies can sometimes distinguish between molecules that differ only in vibrational frequency. It's not conclusive, but it's enough to keep scientists intrigued. Quantum biology is still in its infancy. Most of the field is built on bold ideas, tentative experiments, and more questions than answers. This brings us to a deep and essential question. If quantum mechanics is the true foundation of everything in the cosmos, and if these strange wave states are operating inside leaves, birds, and noses, why does the broader world around us look so ordinary? Why don't we see baseballs existing in two places at once, or find our car keys behaving like a blurry cloud of probability? The answer to this profound mystery lies in a quiet, unceasing process known as environmental decoherence. To understand decoherence, we must remember that a quantum system can only maintain its fuzzy state of superposition when it is perfectly isolated from the outside world. If an electron is left entirely alone in a dark void, its wave function can ripple out smoothly, exploring every possible path and outcome simultaneously. But the real world is incredibly crowded and noisy. In a normal environment, an object is constantly bombarded by a relentless storm of external influences. It is hit by ambient air molecules, struck by rogue photons of light, and influenced by thermal vibrations from the ground beneath it. Every single one of these microscopic interactions acts as a tiny measurement. When a photon bounces off a quantum object, it extracts a tiny piece of information about its position, forcing the system to reveal where it is. For a tiny isolated object like a single electron or an atom, you can isolate them well enough that quantum behavior sticks around for a meaningful amount of time. But for macroscopic objects, things you can touch, see, or eat, decoherence happens almost instantly. The more massive and complex the system, the faster its quantum weirdness dissolves into classical certainty. In fact, decoherence timescales for large objects can be trillionths of a second or less. That's why you don't walk into a room and find your shoes in a quantum blur. Their unceasing violent interaction with the surrounding world has already pinned them down to a definite state before you can even open your eyes. In this way, decoherence doesn't destroy quantum superpositions, it hides them. The superpositions still exist in principle, but they're now entangled with so many environmental degrees of freedom that you can't access or reverse them. They become effectively classical, even though deep down everything remains quantum. This also helps explain one of the long-standing mysteries in quantum mechanics. How do we get from probabilities to outcomes? Decoherence doesn't solve this puzzle completely. It doesn't pick which outcome occurs, but it helps explain why we don't see quantum interference in large systems. Why Schrödinger's cat, if left unobserved, doesn't actually shimmer between life and death on your kitchen counter. Decoherence creates the illusion of collapse by bleeding quantum information into the environment. The result is a kind of statistical consensus. The wave function is still there, but it no longer behaves in a coherent, observable way. And this gives us a bridge between the quantum and classical worlds. Classical physics is still a useful tool. It's how we build bridges, launch rockets, and bake soufflés. But beneath it all, the universe hums with quantum rhythms. What decoherence does is gently veil that underlying weirdness, creating the sturdy world we experience. One helpful way to picture it is like walking on a frozen lake. Beneath the surface is water, shifting, fluid, quantum. But the ice is solid and reliable. Decoherence is what freezes the surface. It doesn't eliminate the fluid water underneath, it just keeps it out of reach. And the more connected an object is to its surroundings, the thicker that protective ice becomes. This also has practical consequences for technology. Quantum computers, for instance, have to fight decoherence constantly. Their qubits are delicate, and even a stray vibration or thermal fluctuation can collapse their quantum behavior. That's why they're kept in ultra-cold, isolated environments to extend their coherence as long as possible. Without that, the quantum advantage vanishes. Decoherence also plays a massive role in how we interpret the theory. Some theories suggest that there's no need for a separate collapse of the wave function. Instead, decoherence explains why certain outcomes appear definite. It's not that the universe chooses an outcome, it's that the alternatives become unobservable due to entanglement with the environment. The tree still falls in the forest, but its echo is drowned out in noise. It's worth emphasizing, decoherence doesn't solve every mystery of quantum mechanics. It doesn't answer why a particular measurement yields a particular result. It doesn't tell us whether the wave function is real or just a mathematical tool, but it does explain why quantum weirdness fades into classical certainty in daily life. It shows us that the world we see is not separate from the quantum realm. It's shaped by it, filtered through a continuous interaction with everything around us. So the next time you pick up a mug or open a door, you can thank decoherence for the fact that it behaves the way you expect, for taking a universe of maybe and presenting it as a firm handshake. It's a quiet phenomenon, no sparks, no flashes, just the slow, graceful loss of possibility, leaving behind the stable patterns we call reality. Imagine setting up an experiment so strange, so delicate, that the very act of deciding when to observe seems to reach back in time and affect what happened earlier. It sounds like science fiction, or perhaps science confusion. But this is precisely what happens in a series of experiments that toy with the very foundation of cause and effect. As we prepare your mind for the final mysteries of our timeline, allow yourself to marvel at how these overlapping ideas hold together. The universe operates with a profound tolerance for ambiguity, letting waves ripple in secret until the environment or a curious device demands an accounting. You are resting safely atop this deep frozen lake of reality, supported by the constant invisible work of a trillion tiny decoherence events, keeping your room stable, solid, and wonderfully secure. Let us now focus our attention on an experiment that pushes our understanding of time and causality to its absolute limits. This is known as a delayed choice experiment, an intellectual puzzle first conceived by the theoretical physicist John Archibald Wheeler. To understand it, we must return to the double-slit setup we discussed earlier, where a particle can act like a spread-out wave passing through both openings when left unobserved, or like a solid particle travelling through just one opening when watched. Wheeler asked a beautifully radical question. What if we choose whether or not to observe the particle after it has already passed through the slits, but before it hits the final recording screen. Imagine a photon traveling toward the two slits. Under normal circumstances, it would pass through them in a state of quantum superposition, acting like a wave. But in Wheeler's delayed choice configuration, a highly sophisticated system of mirrors and optical switches is set up behind the slits. This arrangement allows scientists to make a split-second decision at the very last possible microsecond, while the photon is already in mid-flight, well past the openings. They can choose either to leave the system alone, allowing the photon to land on a screen and reveal an interference pattern, or they can instantly insert detectors to look and find out exactly which slit the photon travelled through. When researchers actually built the advanced laboratory equipment required to perform this delicate test, the physical data revealed a deeply stunning truth. If the scientists chose to insert the detectors at the final microsecond, the photon behaved precisely like a classical particle, showing it had travelled through only one specific slit. If they chose to leave the detectors out, it acted like a wave that had travelled through both slits simultaneously. The mind-boggling implication is that the observer's choice in the present moment appears to reach back in time, retroactively dictating how the photon behaved at an earlier point in its journey. It feels as though the present choice is actively rewriting the past history of the subatomic particle. Wheeler beautifully illustrated this paradox using a cosmic scale analogy. Imagine a massive burning quasar located billions of light years away from Earth. A single photon leaves that quasar and travels across the vast emptiness of space toward our planet. Along its long journey, it encounters a massive galaxy that acts as a gravitational lens, warping the space around it and splitting the light's potential path into two routes, one passing to the left of the galaxy and one passing to the right. After billions of years of travelling through the dark void, that lone photon finally arrives at a modern telescope on Earth. An astronomer sitting at the telescope can now choose either to combine the incoming paths to see an interference pattern, or point detectors at the left and right sides of the galaxy to see which path the photon took. The choice made by that astronomer tonight in a comfortable laboratory on Earth decides whether that photon travelled as a wave around both sides of the galaxy or as a particle around just one side, an event that occurred billions of years ago, long before our planet or the human race even existed. It shatters our comfortable, linear understanding of time, demonstrating that the past is not a rigidly fixed, unchangeable record. Instead, the past remains a fluid state of potentiality until a formal observation in the present pins it down into a definite story. As we sit with this staggering revelation in the deep stillness of the evening, we must transition to the ultimate questions that continue to keep contemporary theoretical physicists awake at night. These are the unresolved paradoxes that signal our current understanding is still far from complete, serving as open doors inviting future generations of thinkers to redefine reality. One of the most famous and fiercely debated of these contemporary puzzles is the black hole information paradox, a profound crisis born from combining quantum mechanics with general relativity. This paradox was first uncovered by the legendary physicist Stephen Hawking in the 1970s. Hawking mathematically demonstrated that black holes are not completely black. Instead, due to the subtle influence of quantum vacuum fluctuations occurring right at the edge of the event horizon, black holes must slowly, steadily radiate energy away into space. This faint glow is known globally as Hawking radiation. Over vast eons of time, this slow loss of energy will cause a black hole to steadily shrink in size until it eventually evaporates completely into nothingness, disappearing from the cosmos in a final flash of light. The immense crisis stemming from this evaporation lies in what happens to all the physical information that originally fell into the black hole. Imagine you take a priceless book containing secret historical records, or a hard drive containing your most cherished digital photographs, and you throw it directly into a black hole. According to the foundational, unyielding laws of quantum mechanics, information can never be truly destroyed or wiped out. The wave function must always evolve deterministically, meaning that if you have perfect knowledge of a final quantum state, you should theoretically be able to reverse the equations to reconstruct its exact past history. Information is supposed to be absolutely immortal, but Hawking's calculations showed that the radiation flowing out of an evaporating black hole is completely thermal and entirely random. It carries absolutely no structural signature or memory of the objects that fell inside. Therefore, when the black hole finally disappears completely, all the intricate information contained within your book or hard drive appears to be permanently erased from the fabric of the universe. This leaves physicists caught in a brutal intellectual trap. If the information is truly gone, then the sacred laws of quantum mechanics are fundamentally wrong. But if the information somehow survives, then Einstein's general relativity and our understanding of space-time horizons must be incorrect. It is a profound contradiction that strikes at the very heart of modern science. To resolve this devastating bottleneck, a radical new concept emerged from the physics community known as the holographic principle. First proposed by Gerard 't Hooft and later beautifully expanded by Leonard Susskind, this principle suggests a breathtaking solution to the information crisis. It boldly claims that all the physical information contained within a three-dimensional volume of space, such as everything happening inside a room or inside a black hole, is not actually stored within its interior. Instead, that information is permanently, perfectly encoded as a two-dimensional quantum blueprint stamped onto the boundary surface surrounding that space. When an object falls into a black hole, its information doesn't get lost in the bottomless interior. Instead, it gets stretched out and captured on the two-dimensional event horizon, like data burned onto the surface of a plastic DVD. As the black hole slowly evaporates, the outgoing Hawking radiation gently sweeps that encoded surface data back out into the broader universe, preserving the absolute immortality of quantum information. But the implications of this idea push far beyond just saving black hole data. If the holographic principle holds true for black holes, it must apply to the entire universe as a whole. This leads to the surreal, utterly mind-bending conclusion that our familiar three-dimensional world, the solid objects we touch, the immense spaces we see, and the very bodies we inhabit, might ultimately be nothing more than a magnificent three-dimensional projection emerging from a deeper two-dimensional quantum code stamped onto the absolute edges of the cosmos. It implies that our solid reality operates like a sophisticated cosmic hologram. The true fundamental physics takes place on the distant, flat boundary of the universe, while we live out our daily lives within the projected interior, mistaking the shadow play for the absolute substance of existence. As you lie perfectly still, resting warmly under a heavy blanket tonight, let your mind gently drift through these immense echoing corridors of modern thought. Maybe you find yourself gazing up at the dark ceiling, your personal thoughts flickering softly like distant stars in the night. Maybe you are currently far away from home, or perhaps you are just far away from finding sleep. Wherever you happen to find yourself at this exact microsecond, my deepest hope is that you have found a sense of profound comfort in this long journey. Something soft, something strange, or simply a moment of perfect stillness. When we choose to stare directly into the hidden heart of matter and ask that ancient human question, what is truly real? Quantum physics does not offer us a cold, rigid, final answer written in stone. Instead, it offers us a mirror, a shifting, shimmering, fluid mirror that constantly reminds us that knowing something deeply does not always mean understanding it completely. It teaches us that the questions we ask can be every bit as beautiful, valuable, and sacred as the answers we find. It shows us that mystery is not a failure of our intelligence, but a beautiful, built-in feature of our cosmos. It can be incredibly tempting to wish for absolute clarity in our lives, to want the universe to lay out its rules plainly, play fair, and match our simple, everyday common sense. But perhaps within this beautifully tangled uncertainty, there is a different, far gentler kind of comfort waiting for us. A quiet truth that whispers, you do not need to hold all the answers to feel completely at home here. Because even if the subatomic particles are fundamentally uncertain, the exact moment you are experiencing right now is completely real. The soft breath you just took into your lungs, the fleeting thought that just drifted through your awareness, the comforting weight of your body gently sinking deeper into the stillness of your bed, that is quantum too, and it is entirely enough. So please accept my heartfelt gratitude for giving your precious time, your listening ears, and your quiet, beautiful curiosity to this slow exploration of our universe. Thank you for trusting the strangeness of the cosmos and for sitting comfortably with the not knowing. And if you have already fallen asleep, sleep well.